a whole day and with a lot of discussion. So thank you for joining us. The title is An Introduction to Technosignatures and Their Connection to Searches for Biosignatures. So in the talks and in the discussions, as much as possible, we really want to see where we see these things as being, basically technosignatures as being a form of biosignature. So we're very interested in the discussions. So the schedule is up here. You can see that we have 4 talks today, followed by discussion, and also a break from 2:45 to 3 o'clock. So you can ask questions, directly. You can ask questions by leaving them in the chat, or on the also on our the Slack channel. Jacob or Ravi, the Slack channel. Where do we need lead people for the Slack channel?
It's technoclimbs.slack.com. I'll put it in the chat.
Okay, so any of those places will be fine. So without further ado, then I will turn the over to Jason. Jason and all the speakers. About at 2 minutes before the end of your time, I will. I'll make a sound either with my phone or some other way. Okay, so take it away. Let me just stop sharing screen.
And while Jason is setting up his screen, I just want to let everyone know that we are recording this. And it will be posted on the NExSS Technosignatures working group page and on the NExSS Technosignatures YouTube, or on the NExSS YouTube channel, as soon as we can get it processed and up.
All right. Well, I'm really delighted to see so many people here. This is great. I think NExSS is the perfect opportunity for our group, the Characterizing Atmospheric Technosignatures group. So that's me, Adam Frank, Jacob Hock-Misra, Ravi Koparapu, and Manas Vilingam, to try and get this connection better established between technosignatures and biosignatures. The two searches have a lot in common, but we don't talk to each other much. So for this particular talk, I will be giving really an introduction to some of the big ideas. A lot of terms you've probably heard before, a lot of terms you maybe haven't. And just to give you an idea of how we think about these things, the language we use, and then also to connect to some recent work that the CATS team has been doing that I think ties some of these ideas together. And I'll finish up with some resources. But what I'd really hope to get out of this is for people to maybe see connections with the work they're doing in the search for biosignatures, or just understanding exoplanets or in general, and to try and find new collaborations, because that's what NExSS is all about. So I'm going to start with this term SETI, the Search for Extraterrestrial Intelligence. That initialism, that acronym, was originally a radio program at NASA, which is where it comes for. It is now the name of the field of searching for technosignatures generally. So those of us in the field don't really distinguish between technosignature search and SETI. It's all basically the same thing, although the term SETI has some heritage in the radio. The term technosignatures is more recent, although interestingly, it was originally coined to include radio. So it was never like a different thing. There's also, of course, the SETI Institute in Mountain View, California, which is a nonprofit research center. But SETI, I like to think of it as just the name of the entire field. There are other historical names for this field. In the Soviet Union, it was communication with extraterrestrial intelligence. Jill Tarter likes to say it's really the search for extraterrestrial technology, because as Dan Wertheimer likes to say, I can't search for brainwaves. I don't know what's intelligent, but I can detect technology. And other people have said, well, if you're looking for radio signals, it's really the search for extraterrestrial electrical engineers. That's what you're after. Amusingly, all of these things are pronounced SETI, so as long as you don't spell it out, you can kind of be agnostic of what you mean. But let's not quibble. It's all just SETI. I think that name has the most heritage, and so that's a term I will use interchangeably with technosignature search. So thinking about this problem of whether we might detect extraterrestrial intelligence is, of course, very old, but maybe the first thread that you see commonly picked up in the modern era of the search for extraterrestrial intelligence is the Fermi paradox. There are a lot of papers on this. It's still a really fruitful avenue of theory and thinking about this problem. It comes from a luncheon in 1950 when Enrico Fermi asked, where is everybody? And they were talking about the possibility of interstellar flight and so on. He wanted to know where they are. You know, the universe is very old. Even if ships are very slow, they should be here by now. And so he was curious why life hadn't spread throughout the galaxy into Earth already. So it's not really a paradox. Some people get upset when it's called that because it's not a formal paradox at all. It's just a question. It's also not really Fermi's. He just asked that question. His name got attached to the idea later after SETI really got going. And if you want a detailed account, Bob Gray has a really nice paper on how it's a total misnomer, neither Fermi's nor a paradox, he would say. But it's fundamentally about why aliens are not here on Earth today. That's what this is about. It's about this puzzle for why aren't they, you know, on the White House lawn, so to speak, since they've had so much time to get here. So if you're going to talk about it, use it in a paper or whatever, the best citations are to an argument by Hart in 1975, Tipler in 1980, and there are a few other papers sort of articulating it. And it was these papers that a journalist actually attached the term Fermi paradox to. So you can't actually cite Fermi for this. Now, this term is often used more generally, so people think that it has something to do with the failure to detect any signals to date. They say, oh, you know, SETI's been looking for 60 years, they still haven't found anything, why not? Now, that can't be what Enrico Fermi meant, because SETI wouldn't have even started for 9 years in 1950. He wasn't thinking about that. It really is about whether they're visiting us here on Earth today. It's often used in that more general sense, which it happens so often it's not really wrong. It's kind of the other Fermi paradox, but I prefer to refer to that as something like the great silence or the eerie silence. But I would actually argue this failure, so to speak, in quotes, to find anything so far, it's not really surprising, because the amount of parameter space that we've looked for where there could be signals out there is so small, we wouldn't have really expected to find anything yet. In other words, the galaxy could be quite loud. It might not be silent at all. We just haven't listened hard enough to hear the appropriate signals. And so in this Cosmic Haystack paper, we did a calculation to try and quantify how loud the universe could be, and we still wouldn't have noticed. And in the parameter space, the 9-dimensional parameter space that Jill Tarter described for just radio, just looking for radio signals, if that 9-dimensional parameter space, you normalize it in volume to the Earth's oceans, then the amount of searching we've done so far is basically a small swimming pool or a hot tub worth of searching. And you would never look at just that much water in the whole ocean and say, I don't see any fish in there. Therefore, the entire ocean is free of fish. That would be absurd. So I would say we can't even talk about an eerie silence or great silence because we haven't looked hard enough. The next thing you'll hear about a lot is the Drake equation. The Drake equation is wonderful. It unifies astronomy, astrobiology, SETI. It's all in there in those different terms. N is the number of things there are for us to find. So he was thinking of the number of radio signals there were to find, but you can reinterpret it as the number of technological species to find. And it's equal to the rate of star formation, the fraction of stars that have planets, the number with Earth-like planets. And of course, we've done a lot of work on those first two, and we think we have them pinned down pretty well now, at least enough for these purposes. Then the fraction of life, the fraction of life-bearing planets that have intelligence. So now we're really into astrobiology. And then the fraction that actually communicate and how long they communicate, and that's where SETI comes in. So this equation has had a lot of variations and reformulations in the literature. It's a popular topic that we see a lot of papers on. It's fundamentally, though, a heuristic. And Jill likes to say it's for parameterizing our ignorance about life in the universe. And in fact, many life in the universe undergraduate courses are basically taught, knowingly or not, with the Drake equation, basically every term being a different unit in that course. So it's proved really powerful and enduring. But in terms of like trying to actually calculate what there is to find, you can't do better than an order of magnitude calculation because we just don't know the latter terms well enough. And so we can do statistical treatments on it, but in the end, it's just going to come down to we don't know. And really, when we succeed in SETI, the Drake equation is going to help us put those numbers in. It's not really going to happen the other way. Also, until recently, no one cited this properly. The citation wasn't even in ADS, but we have managed to get it into ADS. So if you want to cite the Drake equation properly, here it is. But now if you go to ADS and you, and I'll show you how to do this later, you look through the SETI papers and you look for Frank Drake, it'll be the second hit. So you can find it pretty easily. Another foundational figure in SETI is Freeman Dyson, who was thinking about these things right around the time things got started in 1960. He had what he called the first law of SETI investigations, which is that every search for alien civilizations should be planned to give interesting results, even when no aliens are discovered. And he was actually thinking more broadly than just SETI. He had the same opinion when it came to astrobiology. It was important to him from a perspective of salesmanship that, for instance, missions to Mars not entirely be sold as life detection experiments, because when it failed to find life, in his opinion, studies of Mars actually became very difficult to justify at NASA after Viking failed to find life, and he felt that that had been oversold. So his point is that there's a lot of interesting science that happens along the way when you're trying to find life, and you need to make sure that you're advertising that and that you're really celebrating all of the other science. And I think astrobiology does a really good job of this, that there's so much work being done and we're learning so much about life in the universe, even though we have not found extraterrestrial life yet. And SETI can work the same way, building this big corpus of knowledge and learning so much about ourselves and about our targets, even before we find anything. Interestingly, Frank Drake said something very similar right at the beginning. Here he is quoted in 1965, but at Green Bank in the early days. He says, any project aimed at the detection of extraterrestrial life should simultaneously conduct more conventional research. Perhaps time should be divided about equally between conventional research and the intelligence signal search. From our experience, this arrangement is most likely to produce the quickest success. And he was worried about burnout, looking and looking and not finding anything. He didn't want SETI to be an all or nothing experiment. And so this is where I think this collaboration with NExSS can come in really well, is that we are looking for extraterrestrial life, but to do that, we need to connect with other astronomers and astrobiologists, because not only because our searches will be more effective when we do, but because it helps satisfy Freeman Dyson's first law, and we produce great astronomy along the way. So I've categorized SETI and technosignatures. I keep saying it's part of astrobiology. When I think about it, this is the map in my mind. So this is kind of like those old New Yorker covers, like The World According to a New Yorker. This is astrobiology according to someone who works on technosignatures. Forgive that the stuff closest to me is biggest on my map. So this is not by the amount of work done, clearly, but the searches for life in astrobiology is a big umbrella. There are at least two ways to go about it. We can look for biosignatures and we can look for technosignatures. And whether you want technosignatures to be a subset, like inside the Venn diagram for biosignatures or side by side, I'm agnostic to that. This is just how I've mapped it on this slide. So for biosignatures, we know we can look for life on exoplanets. We can look for atmospheric gases in transmission spectroscopy. We could look at surface reflection spectra and perhaps see something like a vegetation red edge or something directly imaged. And of course, the other horse in the race for biosignatures are solar system in situ studies. We can look for microfossils. The Allen Hills meteorite is a good example, or molecular biomarkers. We can, go capture material from the plumes of Enceladus and perhaps see evidence of metabolism in there. Technosignatures, there's a lot of different ideas. I've had fun over the years trying to collect all the different ideas people have had. There are just too many. I list some of them here in kind of a rough categorization. Communication SETI is maybe the one people are most familiar with. We can look in lots of carriers. I'll talk about artifact SETI, which is really just looking for anything that's not communicative, anything that is an object or a thing that we might be able to detect in some way. And then people have gotten very, exotic with lots of things that you might be able to find when you think of really large technology that might be able to alter whole galaxies or stars or something like that. There's also a side branch, the messaging extraterrestrial intelligence, which involves actually eliciting a response by sending signals out. Other versions of that are like the Arecibo message that Frank Drake put out, and even things like the Voyager records and the Pioneer plaques. All of those get us thinking about what it is we think we're looking for and really emphasize the symmetry of SETI, that in order to guess what they might be doing, we have to think hard about ourselves and what our own biases are and what we would do. So you've got all these potential things you could look for. What should we go looking for? And I'm really jealous of astrobiology, which has put so much thought and care into deciding and measuring and thinking about which biosignatures and biomarkers are the most promising, and calculating real detectability for all of them and designing whole missions. SETI in a lot of ways is still in its infancy. We're still sorting these things out, and those are techniques I'd really like to adapt from astrobiology. Sophia Sheikh, who, by the way, just defended her PhD yesterday. Congratulations, Sophia. Put together the 9 axes for of merit for technosignature searches. So here, she compiled all the ways that people would say, oh, that's an interesting technosignature, but I don't think it's a good one because of this. So I think that's a really contrived thing. I don't think aliens would do that. Or yes, that would be really visible, but it's so short-lived. There's no chance you would catch it happening, given how long you'd have to wait to see it. Or yes, that would be great, but that would require all of the world's resources to conduct that search or something. We can't do it. And so she compiled this very nice list of qualitative and subjective metrics for different searches. And it's just a way of letting people sort of apply their own weights to these and their own priors for what they're going to see, and rank which are good ideas and which are bad ideas for things to look for. And a bunch of these will come up later as well. But the ideal technosignature, we could look for it right now. It'd be very cheap. Along the way, we'd satisfy Dyson's first law. It'd be easily detected. It's something that would last forever. It would clearly be technological as soon as we saw it. It's something humans even do. We don't have to extrapolate technology or guess what engineering magic they can perform. It doesn't require any contrivance, like any technological species would do it. And when we detected it, we would learn a lot about them. So those are the 9 axes. Obviously, no technosignatures satisfy all of those, but the more the better. So I'll say a brief word about communication SETI. It's probably a broader field than you think if you haven't learned much about it. In principle, it could proceed over almost any carrier, any of the 4 forces of nature. It could be in the radio, the optical, could be in X-rays. All of those have their strengths and their weaknesses. People tend to favor radio and infrared for what I think are good reasons. But who knows, there could be neutrinos or gravitational waves or cosmic rays. Those are, they don't seem to be very good ways to communicate to us, but we'd of course like to stay open-minded, and maybe there really is something there. So it's fun to explore those. I think those are very underexplored possibilities. Electromagnetic waves really do seem to be the best. The primary challenge is signal strength. Like, 1 over r squared is just brutal. And then discrimination from the background. You can overcome these both by compressing a signal in either frequency or time. And by doing those things, you can keep a signal strong over interstellar distances and easily discriminate it from the background. So what's good about this approach is that detections in principle could be completely unambiguous. There's no way for nature to produce a narrowband carrier wave. That's just technology. As soon as you're sure it's a real signal, it is technology. It could be human technology, but it's definitely technology. And it, in principle, could be content rich. Who knows? Maybe it's got Encyclopedia Galactica encoded in there for us to read. Related to communication SETI, people often think, oh, we're looking for that signal that they're sending us. But it doesn't necessarily have to be a signal that's bright and obvious and intentional for us. That would be the easiest to find. But there's also this idea that we could be looking for leakage. That is communication, or not even communication, radar signals or something like that, that are not intended for us. Those can also be detectable. And interestingly, in principle, the Square Kilometer Array, which is, a big project and it'll take us a while to get there, but the idea is it will get built. it will have the sensitivity to detect our own leaked radio emission if it were that shouldn't say 4 parsecs, it should say 4 light years. 4 light years, 1 parsec away. So that is, if you moved either the SKA or, all of our aircraft radar to Alpha Centauri, you do the math and you do the radiometer equation, and the SKA is sensitive enough to pick it up over the background. This calculation has not been done in great detail, it's order of magnitude, but that's amazing that we are not just sensitive to things deliberately sent to us. In principle, even with our own level of radioactivity, we could detect ourselves at interstellar distances. And that's going to be a new thing that's on the horizon, that we are finally able to detect ourselves at that distance. So leakage has the nice advantage that it doesn't require intentionality on the part of the sender. So it does better on that axis of merit, that it's not as contrived. But it's much harder to spot. So detectability, that axis moves down. So that's the trade-off. Both are reasonable ways to go about doing this sort of thing. On the other hand, if you wanted to search more than the very closest stars, then yeah, that could require this huge extrapolation from our current technology. So either you have to be very sensitive to detect it, or you have to extrapolate an enormous amount of emission. So I said this term artifact SETI as sort of a complement to communication SETI. Once upon a time, this mostly meant solar system work, like looking for literal artifacts in the solar system, going right at the Fermi paradox and saying, well, maybe there are things here, maybe they've been here, maybe we can find them or something. So Ron Bracewell wrote a paper in 1961 about this. But now it's basically just a general term for looking for anything anywhere that's not communication. The nice thing about this is that these could be very long-lived. An artifact can outlive its builder. And so if there is evidence for technology out there, it could last much longer than the species that built it. And so that's nice because it can do very well on the longevity axis, whereas communication might not. So there are a lot of things people have thought about that you might be able to detect for artifact SETI. We made a chart that tries to sort of organize these things. 3 general kinds of things you might look for are physical structures, that's your first row there. Environmental changes, we alter the atmosphere, and that is a technosignature. Or excess heat, the things that we have that use energy, generate heat and give that heat off, that is a technosignature. And then I've categorized these things in columns based on the scale that people have proposed. So you could, in principle, look for these things in the solar system. You could look, hypothesize that there have been intelligent species in the solar system before, but aren't here now. What sort of trace would they leave? It's an interesting exercise that Adam Frank has done to imagine if humans all went away, for how long would our technology be a technosignature in the Earth's geological record? And the answer is not very long. So our horizon into the Earth's past and the solar system's past for technosignature is actually not very long. And there could be things that aren't obvious at all. There's exoplanetary things. We could look for satellite belts or large megastructures in orbits at Lagrange points around other planets. There are environmental changes. We might be able to see the effects of industry on other planets. And then circumstellar things, you've heard of, transiting megastructures. You could imagine that stars could even contain contaminants that might be technological. And then if you have enough of those things surrounding a star, you could have excess heat from something like a Dyson sphere. So lots of ideas. It's important when we go looking for these things, though, that we make sure we're constantly making progress. And one of the difficulties of the earliest searches for radio signals and other kinds of things is that all that we know about them is what instrument they used and that they didn't find anything. And that can make it very challenging to do anything with that. And we need to make sure that we are markers of progress as we look for those things. And so this is one of my hobby horses that we need to get better at in SETI, which is that we need to set good upper limits. And the reason, of course, is that most searches will end up with no good candidates. And this is not a problem unique to SETI. Of course, we have that in the searches for biosignatures and fields like particle dark matter detection, for instance. This is very common. Most searches fail to find the dark matter particle, but they still make good progress and they're still doing good work. So the fact that we're not going to find anything most of the time does not mean that this is an all or nothing project any more than it means those other projects are all or nothing. The key is to report what it is that we found did not exist. Because it's not just we didn't find anything, it's that we showed certain things were not out there. And if we can keep expanding that pool of things that aren't out there, not just the hot tub, but much larger volumes of water, then we can mark our progress. And in general, when we do our searches, we need to tune them to generate a manageable number of candidates for follow-up. The neat thing about technosignatures is that there are things that shouldn't be able to be generated naturally, or that are extreme in some way, which means that, whatever our most extreme things are, they're going to be interesting. So this is the way I often think about this. This is a little heuristic. So the y-axis is the strength of a technosignature signal that we're looking for. So perhaps we're looking for Dyson spheres, and this is the infrared excess of all of the stars in our catalog. There is some upper limit, right? There is some, most infrared bright object in the sky. And so once you know what that is, you've set your search upper limit. There are no Dyson spheres that are more complete or warmer than this thing. And then you tune your search limit, your anomaly threshold, down to get some manageable number of candidates. And now you have things that, could be SETI signals, could be technosignatures, or more likely are very extreme natural objects. And now you're doing really interesting astrophysics. Why are these objects so extreme? What are they? Have you found anything that's new to science, and so on? And so I think it's important that in SETI, we keep this in mind. I think this also helps perhaps when we work with experts. So if I'm going to go look for Dyson spheres, I need to work with experts on infrared stars, debris disks, and these things, because they're the experts in the objects that I'm looking at. If we want to do things like think about technosignatures in the solar system, we need to work with planetary scientists who understand these objects and assure them that, we're not trying to pull a face on Mars here. We're trying to set interesting upper limits. And when we do that, even the SETI skeptics that think might be a waste of time, well, if we say, well, then we won't find anything, and we'll set an upper limit, and now we'll have shown what your prior tells you, which is that those things aren't there, and we'll have a good paper on it. So I think this attitude is very inclusive and will help us do our work better. Okay, one term that gets tossed around a lot with SETI is extraordinary claims require extraordinary evidence. And this comes up, of course, in the search for biosignatures too. And when strong claims get made about the detection of biosignatures or technosignatures, they can get a lot of press. And so I think it's important to say up front, what our perspective is on this claim, and what we think about those sorts of specific claims about things potentially being technosignatures or biosignatures. So my perspective on this claim is that it's just Bayes' theorem. If you want to overcome a very small prior, you need a lot of evidence. Well, an extraordinary claim, what does that mean? It means that you have a very small prior on that claim. And so this is just, Bayes' theorem for things on which you have very small priors. It's not, it's a rigorous way of thinking about science. But I want to point out that as scientists, we need to be constantly reevaluating our priors because they're not always well-founded. They're not always based on any kind of evidence. Is the claim really extraordinary? After all great discoveries at one point were thought very unlikely. So as an example of a prior that you might want to reevaluate, let's take the prior that we are not the first technological species on Earth. That there was some prior species of Earth life that had technology. Now, if you had asked me 5 years ago, my prior on that would be basically 0. We would have known such a thing. How could they have hidden? But then Gavin Schmidt and Adam Frank did this work, and what they showed me was that, in fact, our evidence horizon is very low. That prior I have is not informed by evidence. I still think it's very unlikely. But now that I've appreciated that there's no evidence for a lack of previous technology, I think it's a little more likely than before. Still an extraordinary claim, but not as extraordinary as perhaps I thought ahead of time. So when a new phenomenon is discovered and it's explored as a SETI target, Oumuamua got a lot of attention, Tabby star got a lot of attention, or there's a biosignature claim like phosphine on Venus or something like that, I think it's important to distinguish between different kinds of claims. There's a claim that the posterior on it being a detection is large. This is the extraordinary claim. So Oumuamua is an alien spacecraft, is an extraordinary claim. Tabby Star has a Dyson sphere, would be a very extraordinary claim. But if the claim is just that our prior was too small, if thinking about Oumuamua as a spacecraft makes us re-examine that prior, whether or not it is, and it is not, then that's a different kind of conversation. And sometimes it's hard to have both of these conversations at the same time. So I'm hopeful that even the SETI skeptics will keep an open mind, not because we think we've found aliens, but because a lot of the preconceived notions we bring to this field sort of don't hold up once you challenge them and once you think about them. So that brings me to maybe the most contentious part here, which is the likelihood of biosignatures versus technosignatures as being the way we find alien life. Both are completely reasonable ways that we might succeed in this shared endeavor that we have. But the relative likelihood, I think, a lot of people will say it's got to be biosignatures, and they have reasons that seem very good, but I'm going to argue that I think these should be about even in your mind. They're about even in my mind. I really don't know which one is more likely to succeed. So let me make my case. So the first argument that biosignatures might be more abundant, or technosignatures, detectable, comes from abundance. So if you think about the Drake equation, it would seem to imply that the number of technosignatures there are to find have to be less than or equal to the number of biosignatures there are to find. And that's because that fraction f sub I, actually the product of f sub I, f sub c, is got to be less than or equal to 1, because it's a fraction, which means there have to be more places with life than there are places with life that are communicating or doing technology. After all, most of Earth's history was that way. And that seems pretty robust, but there's a catch, which is that this assumes that technological life does not spread. Remember the Fermi paradox, which assumed technological life was going to spread. Why aren't they here right now? The Drake equation is all about life that stays put. So the Drake equation, in some sense, is the opposite of the Fermi paradox in its assumption about whether life can spread. If technological life spreads, then it's very possible, in fact, that the number of technosignatures to find is much greater than the number of biosignatures. That is, the sites with technosignatures versus the sites with biosignatures. And think about the solar system. What is the number of sites of biosignatures in the solar system? Well, it's probably 1. And if it's more than 1 because of Mars or Enceladus, those biosignatures in those other places are not easily remotely detectable, certainly not at interstellar distances. But the number of sites of technosignatures in the solar system is more than 1. Mars is literally crawling with robots, and those robots are giving off radio waves. We have 2 planets, at least, in the solar system with technosignatures detectable at least at interplanetary distances, and with a bigger enough telescope, interstellar distances. So we've already got more technosignature sites than biosignature sites just with our technology. Another point is that think about Mars in the future. We are going to move there. So then, yes, I presume eventually someday we will move there. At which point, yes, there will be biosignatures there. But the idea of it having a biosphere, remotely detectable biosignatures, I'm not sure. Are we really going to terraform it? We don't have to. It could just be all bases and underground and so on. And in that sense, you would have a world of technology that was not sustaining a biosphere. Which means if you don't have to worry about sustaining a biosignature, the technology could be quite large. And so there's this idea that Manosfi is putting together in a paper about service worlds, which is a world that's used entirely for technology that doesn't need to support a biosphere and does not support a biosphere. So it's all technosignature, no biosignature worlds. And those are in fact the ones that we might see most of. They could have very strong technosignatures. There could be a very large number of them. And so that, I think, argues strongly for strong abundance. So just to give you a sense of how many of these there could be, let's make the Fermi paradox quantitative. So let's assume very conservatively that spreading to nearby stars is rare. maybe it assumes it happens every 100,000 years for a technological civilization. Let's say that only the nearest stars can be settled. So the farthest any ship can go is about 3 parsecs. So that could be the sort of speeds our things go, and they just take 300,000 years to get there. Or maybe they're going super fast near the speed of light and it only takes a few decades. Either way, let's say you can only go about 3 parsecs. This is a movie that was put together by Jonathan Carroll Nellenbach as part of a collaboration with Adam Frank and others. And what you're seeing is a model of the galaxy. And those magenta points here that you can see, those are settlements spreading. We've had to scale up because of the number of stars, but the range here is 3 parsecs. And so they are not allowed to spread more than once every 100,000 years. They can only go to their very nearest neighbors. But because the stars move around, they occasionally spread things out. And these settlements don't last forever either, but then they go back and get filled again. As soon as they reach an area of high stellar density, everything takes over in exponential growth. R naught is greater than 1. And things spread. So that's the Fermi paradox. Why hasn't this happened? And the answer could be, well, it has happened. There are service worlds and technology everywhere. So you don't have to believe this story. But I hope I've at least moved your prior on whether it's possible that there are a lot more sites of technosignatures than biosignatures, and argued that it's very plausible and that you shouldn't dismiss SETI because there just won't be that many things to find. All right, longevity. We get this one a lot as well. The Drake equation would seem to argue that there's fewer technosignatures than biosignatures because they don't last as long. Because intelligent life, by definition being a subset of other life, can't last as long. But again, first of all, this is only true for Earth's past. As far as we know, we're the first technological civilization, and looking backwards, we're just this tiny little blip in Earth's past. But of course, we don't know what the future holds. Humanity is the first species that can prevent its own extinction, which means the upper limit on how long we could be here is much longer than any other species. Even a cataclysm like a nuclear war or catastrophic climate change, that doesn't actually change this at all unless it makes humans go extinct. Because even, if it's all post-apocalyptic for a while, as long as someone survives, we're smart, we've got the technology around, we'll come back. So it's only things that cause human extinction that would limit us on Earth. Also, remember, there are other tool-using intelligent species on Earth. So even if we did go extinct, that doesn't mean that some other species wouldn't, get their opposable thumbs and pick up where we left off, or that we're not picking up where someone else left off. And even if we are especially self-destructive, and it's just a thing about technology that we're self-limiting, it doesn't follow that every other technological species will be. That movie I showed, there was only one spreading technological species. That's all it took. That wasn't horribly self-destructive. So I think it's very reasonable to hypothesize that intelligence lasts just as long or even longer than other kinds of life. I hope at least your prior has moved in that direction at any rate. And I'd encourage you not to let your anthropocentric biases about the way we think of human intelligence bias you about what other kinds of intelligence and technology might be like. Okay, ambiguity. If I'm going to go look for Dyson spheres and stuff, that's just, they look just like debris disks. I'll never know exactly what I found. So yes, many technosignatures are quite ambiguous, but of course, this is also a major problem for biosignatures. And this is a young field, technosignatures. And so I'm hopeful we can do the same sorts of work that biosignatures has done to work on this problem, which I think is not fatal, it's manageable. Also, I should point out some technosignatures really are absolutely unambiguous. Narrowband optical radio infrared pulse signals are absolutely technological. Pulsed emission is almost certainly technological. There are exceptions, but we understand how to manage those. And then there's another one, things like artifacts in chemistry. CFCs and other synthetic chemicals have such small biogenic sources that they and they're so easily destroyed that if they're in any concentration, they're certainly technological. So then another argument is strength, that, yes, we have technologies, but you just cannot see those at interstellar distances, whereas the effect of life on Earth's atmosphere is detectable at interstellar distances. And that's true, but it's still pretty weak. It's still pretty challenging. Most biosignatures are pretty subtle because terrestrial planets' atmospheres are pretty subtle. And they have to be pretty subtle in the solar system, or we would have seen them by now with the Hubble Space Telescope or something like that. Technosignatures, on the other hand, have no upper limit here. They can be almost arbitrarily strong. So if we have flat priors for how strong they can be, we've got a huge amount of space that makes them extremely detectable. Also, Earth's technosignatures are already probably more detectable than its biosignatures. For instance, we have lasers. A 10 kilowatt laser can outshine the sun. And if you resolve the Earth, you only need 10 or 100 watts to be detectable at interstellar distances if it's behind a big enough telescope. A 1 megawatt radar, for instance, our interplanetary radar, that's detectable at interstellar distances. And not far in the future, if they ever do that breakthrough starshot thing, that's actually visible across the universe. It's so bright. So Hector Silcas Navarro put together a neat idea called an ICNOS scale. It measures the scale of a technosignature. It's basically its strength. With humanity's technosignatures today normalized to 1. So all of our technosignatures are 1 on this scale. So if we think of this as a new axis of merit, the best ones are detected at very low ICNOS scale values. So radial leakage from Earth has ICNOS scale 1, and the SKA will finally be able to detect ICNOS scale 1 leakage when it comes online. And so the question I think that really will crystallize the search for technosignatures in many people's minds is what other technosignatures at ICNOS scale 1 are detectable? ICNO, by the way, this comes from the Greek. It basically means footprint. What is the footprint of the technology? So this is one thing we've been working on in the CATS group, the atmospheric technosignatures. So I want to show some of the results that we've gotten here because they're pretty amazing. So a nice thing about looking for atmospheric technosignatures is that we can do this simultaneously with biosignatures. We're looking anyway. So that's one of the axes of merit. Also, many artificial gases have no significant abiotic source. That means that they're unambiguous, as long as you're sure you know what you're looking at. So it might be ambiguous whether it's a CFC or not, but if you know it's a CFC from the spectrum, it's definitely technological. So let's look at CFCs and NOxes, and those are the two of the things we've done here. So Lin et al. In 2014 looked at the possibility of CFCs in the atmosphere of a transiting Earth-like planet around a white dwarf with James Webb Space Telescope. And Webb, it turns out, could do something like that in days. So there's a lot of ifs there. You need an Earth-like planet around a white dwarf with technology, but still it's not impossible. Jacob Hock-Misra and our group has been working on looking at CFCs around terrestrial planets that we might look at with the James Webb Space Telescope in maybe more realistic situations. Most of the absorption is in the infrared. Here are some spectra for those who like that. The bottom line was that TRAPPIST-1e, we could detect ICNOS scale 1, Earth level CFCs in 300 hours of web time. Now, that's a lot of web time. It's less than needed for some biosignature gases, though. So we are now on the same playing field here as biosignature gases around one of the best web targets. So that just blew me away, that this technosignature is right up there with biosignatures that we're considering. Now, 300 hours of web on TRAPPIST-1e is a big ask, probably not going to happen.
Jason,
yes.
3 more minutes.
Understood. Anyway, we then moved on to NO2 and NOxes. NOxes are a technosignature. They are produced during combustion. And the bottom line there is if you want ICNOS scale 1, we're talking about 600 hours with LUVOIR, 15-meter LUVOIR, if you want to do that. So again, a huge amount of time, but also if there's more NOxes than we make, that makes it more visible, and it puts us in the same ballpark as biosignatures. Thomas Beattie had a really fun paper on city lights. The question is, could you detect city lights if they're the same kinds of city lights humans make, because you need to pick something? The answer is at ICNOS scale 2000, yes, you can. So this is again with LUVOIR A, and sure enough, at Tau Ceti rocky planet, rocky planet, habitable zone around Tau Ceti, you could see an ICNA scale 2000 set of city lights. Now, that would be what's called an ecumenopolis. That means the entire planet's covered with a city. But again, if it's a service world, if it's something like, a place they moved like Mars, then maybe that's not actually all that silly. So the bottom line is technosignatures could easily be longer lived. They could be more abundant. They could be more unambiguous, and they could be more detectable than biosignatures. At the very least, it's possible. And I hope your prior on that will be nice and flat after hearing our arguments. All of that more than biosignatures potentially. So I think we should go check. So I'm going to close with some resources for people who would like to learn more and get started in addition to what we're doing here in this webinar. We had a paper on the jargon. We use a lot of jargon because we're a scientific field like anyone else. So there's an ad hoc committee on SETI nomenclature, Wright et al. 2018. I encourage you to start there. You can search for SETI papers on ADS. There's this magic keyword, it's not advertised well, called bibgroup. Bibgroup:SETI, and then the rest of your search, and everything you get is a SETI paper. We curate this here at Penn State. Every month, we send our new list of things that have been added to the bibliography to SETI.news. If you'd like a newsletter that has all of the latest papers from the previous month in SETI, there you go. Please go to SETI.news and sign up. There's the Slack. There is an IAA community mailing list. There are 3 ongoing seminars that at least this last semester were online. And Adam, Ravi, Jacob, or I can get you onto any of these if you like. And please come to the Penn State SETI Symposium. It will be next summer, 2022, in June, in Penn State. It's going to be great. It's going to be 4 days of SETI, 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 SETI. And then finally, I taught a graduate course in SETI here at Penn State. If you just try to Google the Penn State graduate course, you could go there. There's a whole page there that's the papers we read. It's basically, I think, the canon of the field. And so that's a good place to go to get references on any of the ideas that I was just talking about. And with that, I will finish up, and we want your ideas. Let's find out how we can collaborate on this.
All right, thank you very much, Jason. All right, so I will turn it to Ravi and Jacob to moderate the questions.
Okay, thank you, Jason. So if people have questions, please raise your hands and we can go through that. We have a significant amount for time for discussions. So if you want to raise your hands, there is a reaction button at the bottom. You can see an emoji and there's a raise hand.
Lucian, I see, has a question. How are papers added to the big group? Giles' work is not even mentioned. Oh, I don't know how we missed, Lucian, I don't know how we missed Daniel's papers. You can send me an email and I will make sure it gets added for sure. And I mean, if anyone wants to take on the work of helping us maintain it, it's a group editable bibliography. So I'm also willing to take volunteers there. But yeah, if we're missing anything, please let us know.
David.
Oh, and Macy's in the chat. She can add them as well.
Go ahead, David.
Me? Yeah. Yeah, I had a question. I mean, great job, Jason. You really did a great job at expanding the space and showing how these priors should be very agnostic. And I guess I'm sort of playing devil's advocate here, but I'm wondering to what extent that uncertainty, it could also hurt the search for ETIs, because biosignatures might have a more constrained direct case that they are looking for more of a specific signature, whereas we're kind of waving our hands a bit, saying, well, this might be possible, this might be possible, this might be possible.
Yeah, no, I hear what you're saying. I think I would answer, appreciating that it's a devil's advocate question, that the reason biosignatures are constrained is because they've done the work of winnowing things down to what's detectable. And I think if we were having this conversation 15 years ago, that might not have been the case. Like, what are we going to do? What are we going to find? And there might have been a lot more ideas. we now have calculations for what it's going to take to detect methane and oxygen around specific exoplanets. But those calculations are building on over a decade of development by a lot of people on this field. And that's because NASA has nurtured astrobiology in a way it hasn't nurtured SETI. So my hope is that if we look at SETI 10 or 15 years from now, assuming we haven't found anything yet, that it will be more clear which of those things on my huge laundry list are reasonable to look for, and which ones maybe have already been ruled out, or which ones are just too fluffy.
It looks like
Even biosignatures are constrained by life as we know it.
it looks like Yaman has his hand up.
Hi, yes, Jason, really good talk, we enjoyed it. I've just got a question about the evidence and how we present or rule out certain classes of evidence. I just get the feeling that we have quite a binary nature, in the sense that a lot of evidence we see is so kind of controversial and not substantial enough to form a proper scientific basis. And on the other hand, with good reason, we kind of rule out all kinds of evidence because there's a lot of people out there that want to claim aliens when it's just fraudulent, or nature plays a lot of tricks on us because we don't have a very good feel for what the kind of signal we're looking for.
Mm-hmm.
So I'm kind of wondering whether there's scope for some sort of almost like a Torino scale for levels of detection, the kinds of different kinds of detection where we could say in scientific papers we have a grade N detection,
like
or
the Rio.
we rule out grade N detections at certain signal to noise or whatever. Do you think that would be useful?
Yes, it's called the Rio scale for SETI, and it is a way to evaluate the strength of a detection in SETI. And I think it's partly like the Torino scale there to help, say, the press interpret, but also our colleagues interpret how much evidence we really have for something. So the original Rio scale was adopted by the AAA Permit Committee on SETI. It doesn't get that much use, it should get more. And Duncan Forgan and others, including me and Jill Tarter, worked on a revision of that we think is a stronger version called Rio 2.0. And it's really about SETI specifically. And then getting more to your point.
9-dimensional parameter space? I mean, is it a multivariate measure?
There are a series of considerations that go in. It attempts to be general, and it has to do with how sure you are the signal is real, how unambiguous the signal is, could there be confounders, could it be fraud, all of these things. And it tries to put things onto a scale with 10 being you're absolutely sure it's real, you're absolutely sure it's aliens, it's nearby, you're communicating with them. That's a 10. So take a look at the Rio 2.0 paper by Duncan Forgan et al. Okay. And then I just more generally about evidence, it can be difficult working in SETI to talk about candidates, like cool stuff like Oumuamua and Tabby Star, without people misinterpreting you, or incorrectly interpreting you in some cases, as claiming you have found aliens. And so it can be difficult to thread the needle of, here's what we're looking for, here's a good candidate, it's interesting, let's studying it, versus crying wolf and playing the face on Mars game and so on. I agree that's a tricky thing, but Biosignatures has it too. Allen Hill's meteorite, phosphine on Venus, a lot of nuance in those stories got lost in the media. I also want to highlight Evan Sneed in the chat points out I missed an important conference. If you are an early career researcher interested in SETI, there is a conference this summer. Find Evan's link in the chat and go join the Order of the Octopus. He can tell you more.
Okay, there's been some great conversation in the chat. If anybody wants to unmute and ask Jason a question that you posted in the chat, please feel free.
Jason, I have to run it too. This is Casey List, but I will ask you controversial direct question. If you had to pick a system or two that you think would be most interesting to go after, or you think you have your best technosignatures information or signal from, what would you, if you were a betting man, which would you go after right now?
You mean which technosignature?
Or yeah, or which signal we already gotten that you think is worthy of following?
Oh, I don't think we have any good signals to follow up in SETI. I think the WOW signal is probably the closest. I'm going to dodge with the truth. I'm going to give a truthful dodge to your question. I don't think we've done enough work to know which technosignatures are the most promising yet. I think once we've developed them all at the level of radio is, we can make that assessment. So I'm going to work on the things that I find interesting, and my own personal biases tell me that I can help the most with. And I hope you all do too.
And I understand the hedging, if you will, but it's also sometimes useful just to make or show it or talk about real world examples or not.
I think we can make the most progress right now with things like Dyson spheres and laser flashes. I think there's a ton of low-hanging fruit there. It will not take many person hours to put firm upper limits or make a detection in those two directions right now.
So you'd, for example, go after wavelengths like neodymium YAG lasers or argon lasers that you think could possibly just be easy layers to make, or CO2 lasers, easy things that are easy to make powerful, that somebody could just have been using in their technology and not thinking about the fact that they could be shining out in the universe.
For the lasers, I think it's most likely they would come from deliberate communication if they exist at very short timescales, like nanosecond. But you can also imagine unintentional leakage of those sorts of things, or just that, they're not broadcasting to us, we're just, in the way. Plus, I think, short flashes in the sky is a hugely unexplored part of astronomy. I mean, sub-millisecond temporal variations is just, it's terra incognita. And so I think Penn, Shelley Wright and Paul Horowitz's project is just gonna, the parameter space they're exploring is enormous. And I expect they'll find a lot of really cool things, pulsar giant pulses and things like that.
Jason, can you show the slide which showed the intro to the field? Suketu is asking.
Sorry, which side?
The introduction to the field slide.
The reference is about the intro to the field.
References above sorry. I'm not parsing the words.
Yeah, the one just before that.
Yes.
Yeah, thank you.
Can I also make a comment? If there's nobody, I don't want to step on anybody.
Thanks.
What have you got, Adam?
Well, I just wanted to point to that question about, what's most promising. I just want to emphasize, while it might not be the first thing you would do tomorrow in terms of a search, but in terms of characterizing, I think there's all this work to be done in terms of systematizing the work, which, lots of great work was done over the last 15 years with biosignatures and is only now being able to begin with technosignatures. And so the results that Jacob and Robbie, sort of led from our group about that Jason showed about the CFCs was really, I mean, for me, it was startling that, here's an industrial compound which wouldn't be in the atmosphere on its own. Well, at least you have to come up with reasons why it would. And that we could detect from, interstellar distances, our own concentrations with JWST. So I think this idea of characterizing a lot of the work that has to be done right now is just trying to figure out what are good technosignatures on Sophia's axis of merit, things that over the next 5, 10, 20, 30 years, we really would have a hope for being able to find. And I think, there's this enormous, not just more than just what you would go look for tomorrow, but there's also, what work we can do now to figure out what you should be looking for. And in that ways, I think over the last few years, we've made some pretty remarkable progress.
Looks like Daniel has his hand up.
Yeah, thanks. Very nice talk, Jason. I had a question about target databases and synthesizing data and observations on targets. So I understand that there are not many strong candidates currently, but it strikes me that it may be useful to try to collect attempts and any potential candidates that were, even if weaker candidates, from different searches, and integrate them into a single database, so that future observations can be guided by those. And when we are interpreting, for example, a potential candidate, we would have a history of past potential detections of the same system with different techniques by different teams. So can you tell us maybe briefly about what effort has been put there and what?
Yeah, no, that's a really good question. So the Jill Tarter has done a lot of work to just try to compile like the lists of the searching that's been done. And as I said, many early searches didn't even say what their target list was. They just said we looked at 100 stars and didn't see anything. And so even just listing how many stars and getting that all together has been a challenge. But now that is up, and the website is called Technosearch. I think it's Technosearch, and it's hosted by the SETI Institute. In many cases, there are then links to what often little documentation exists for those searches. And some of those, especially the big recent ones like Breakthrough Listen, have cataloged all of their targets. Most of the searching done to date has been radio, and radio does tend to be all or nothing. You are not like, ooh, that's right at the threshold of detection. Is that maybe a signal? I have 10 million strong hits. They're almost certainly all RFI. How much filtering can I do before I'm down to 0? And then if you back off on your filter, you're not looking at weak, maybe aliens. You're looking at just weirder RFI. So I'm not sure we're going to get many maybes from the radio, except transient things like the wow signal, perhaps. And then as far as the other ones go, the laser searches, there have been a few good ones. Actually, the very best laser search, two of the laser searches, their top candidate that they rejected in both cases was, of all things, Tabby Star. So I think Tabby Star might be the only target that has had maybes from multiple detection techniques. I don't think it's a good SETI target at the moment, but it's a good idea, though, to try and synthesize. I guess my answer, a long way of saying it, is that feels like a kind of a pro move, and we're still kind of getting the foundation for that. I just want everyone to report an upper limit first, and then tell us your target lists, and then maybe you can start ranking things.
Thank you.
So that was one. Jill, do you want to speak up, because you have some very good points in the chat? Jill or Lucian, both of you. Maybe we'll start with Jill.
Yeah, I think that since the number of candidates, quote unquote, signals that you could report increases exponentially as you lower the signal to noise threshold that you impose, I think it's going to be really hard to try and compare or use results from different searches. We've tried to do that in the past, and we haven't had much success. And then the other thing that I was going on about in the chat, excuse me, Jason, but please call it Boyajian Star, not Tabby Star. If she wasn't so attractive and young female, we would never have used just her first name to name a phenomenon.
Thanks for that, Jill. Yeah, indeed. That's why I called it Boyajian Star in the paper.
Good.
Lucian, do you have any comments? I know there was quite a bit of discussion going on. Any thoughts? Tessa?
Well, there's some comments that Paul Davies asked about. I'm sure I won't say this right, but Sobilsky's star as a technosignature. I know Jason has some thoughts about it.
Sobilsky's star. So yeah, what's the question about Sobilsky's star? The Sobilsky star is a slowly rotating magnetic early after late A star, and its spectrum is inexplicable. it is just a forest of absorption lines, and almost all of them are unidentified. The standard explanation is that it is experiencing, has a very still atmosphere, it's experiencing heavy amounts of radiative levitation, which sorts elements, and for whatever reason favors heavy elements like lanthanides to be high in the atmosphere where they can collect and we can see their absorption spectra. And we just don't have good line lists for most of these elements. These are the kinds of elements that you only hear about, like, you know, in the Tom Lehrer song or something like that. So it's been suggested that perhaps they are the products of some sort of artificial nuclear reaction, or that they are decay products from island of stability out at high. And I don't know, it's a real astrophysical anomaly. I'm not sure it's necessarily a SETI anomaly, but it's a real puzzle. But I think, unfortunately, the progress on that particular target, well, not unfortunately, I think the direction to learn more about that is to get physical chemists to measure spectra of, you know, protactinium at 3000 Kelvin. And that's a tall order. Or else get the quantum chemists to get better theoretical predictions of those transitions. So, you know, not glamorous stuff behind a telescope, but it's a really cool puzzle. I'd also point out that Macy has already added Daniel Giles' papers to the SETI-BIB group, and so it should show up in searches the next time they refresh at ADS, which is kind of weekly, I think. David Kipping wants to know if there are any news on BLC1. I don't think so. The paper's moving along. The team is pretty sure it's radio frequency interference. It looks a lot like radio frequency interference now that they've analyzed it much more closely.
Looks like Sean has a question.
Yeah, somewhat of a shout out to a talk coming later from Niki Parenteau, which I'm really looking forward to, because I think if I were to draw two distinctions between biosignatures and technosignatures, and I'm sorry if you covered this, Jason, and I did not hear it, but I didn't hear. One is the way that the Drake equation might be kind of a silent prior in our heads, in that we've kind of, not to be used to estimate how many civilizations are out there, but just we have historically kind of marched from left to right in those various terms in that equation. And the next one is the biosignature term, and it's coming after we've gotten a handle on the abundance of potentially habitable worlds from TESS and Kepler and other and ground-based observatories. And so in that sense, that might be something that's in all of our heads, that there's this expectation we do the biosignature search first and then do the technosignature search in an intentional way. And the other point, which gets to what I hope we'll hear about from Niki, is the research into astrobiology that's been going on for decades is much broader than the research that goes into biosignatures specifically. I'd say that I've probably learned more from more than anything else from our colleagues that do like biogeochemistry and swim around in stinky sulfurous ponds, who have helped us understand why biology does the things it does in specific environments. And it's that kind of foundation from which we're going to be able to understand how to do a generic search for biosignatures. I see Tessa Fisher's been active in the chat, and she's one of the people thinking about this, of how do we get to, a generic or agnostic biosignature and a statistical one. And so I guess my question would be, other than please watch Niki's talk and pay attention to that. My question is like, what would be that kind of contextual research, right? Like if for biosignatures, the contextual research is biogeochemistry and how biology acts in a planetary context. What's the research outside of research into technosignatures themselves that would be required to advance sort of the theoretical groundings for technosignature work?
It's a great question. I think technology is a product of society. And so in addition to just understanding technology and its limits, we also have to understand, why we make it, what it is for, and, look both at why we think we're making it and what we're actually doing with it. And so that means engaging a lot in, I think, the social sciences, understanding technology in society. And I think that's actually super valuable. A lot of SETI work, people say, oh, the aliens are going to do X, Y, Z because that's what we do. And then I'll talk to a social scientist who says, no, actually, that's not how humans use technology at all. That's a very narrow view. And so a lot of the assumptions that we make in SETI come from what we think we know about humans and human technology. And a lot of those things you think you know are myths, and that social scientists, anthropologists, for instance, can help us dispel a lot of those myths. And I think that is a valuable way of looking forward. And when we project humanity into the future, we think about these future studies. That's another aspect of that's another field that we can access, thinking about what the futures of humans in space looks like. So I guess what I'm saying is, in the end, it comes to this symmetry that SETI sets up, that we're looking for something kind of like ourselves. And so if we don't even understand ourselves, then we're kind of hopeless at trying to find something else out there. So I have found working with anthropologists and futurists in particular to be valuable.
I wonder if Catherine Denning, who I know was on before, has any additional comments on what Jason just said. So I don't know.
Catherine is on. Yes, Catherine, jump on in.
Hi, everybody. Sorry, can you hear me okay?
Yes, thank you.
Great. Thanks for the invitation to comment. Yeah, just, seconding on what Jason has said. I think one of the difficult things about trying to project evolutionary trajectories and things like this is that
you keep dropping out, Catherine.
Sorry?
You keep dropping out. I don't know if you can.
Oh, sorry. Yeah, I have a somewhat wobbly connection here, so maybe I'll just add a quick note in the chat and address it that way. But anyway, thanks for the invitation.
So we have a few minutes left. I see Glenn has his hand up.
Yeah, I guess everybody, when they have a research project in SETI, they have an axe to grind that they don't want to bring forward. But one particular thing that I'm interested in the NSF astronomy, which my domain is interstellar medium, is really where the chemistry of life begins. So I'm sort of looking for simple binary questions, like, did all of the chemistry for life actually happen in the interstellar medium, or could you argue that? Or does it actually happen in a pond on a planet, which is not my domain, so I'm less in favor of that, but only because of this crazy axe I want to grind, is that I would like to see somebody answering that kind of question. Is all of the chemistry really needed, ready to go when it drops on the planet? Or so that's just one area that I particularly am interested in, and would happen to be happy to see somebody address that question well. Anyway, so that's just one sort of maybe tangent to the main activity going on here, but it interests me anyway.
Cool, thanks.
All right, Daniel has his hand up, and that might be the last question for the session.
Yeah, I just wanted to raise a topic that I think we didn't cover too much, but I think it's interesting in a strategic sense. So there's clearly a very large, and I think you made an excellent point, how large is the discovery space that is available to different techniques. And I wanted to bring up the point, or raise the question about both the scalability of the technology that we can use and the temporal evolution of that. So just to put it, as you contrasted it with biosignatures, in order for us to expand our capabilities, to scale up our capabilities, search for biosignatures, it requires a very significant investment and decades of development of new technology. And that's certainly true in some cases. For example, the atmospheric technosignature signals that you mentioned, but it is probably not the case for things like radio, where we obviously can benefit from technological electronics evolution, computing power. And I was wondering if you want to address that, or others want to to add to it, what is, if we project to the next 20 years, what are the range of possibilities in terms of the growth of capabilities and the fraction of the discovery space that we can capture with technologies?
Yeah. Yeah, it's a good question. It's a little challenging because, if I take my laundry list of technosignatures, it's just all over the map. But if we talk about the ones that are more developed, I know Jill likes to say that the Allen Telescope Array is a Moore's Law telescope. So, the speed with which you chew through the discovery space is proportional to your processing power, depending on how you define things. I think, fortunately, a lot of searches for technosignatures can be done concurrently with biosignatures. It's particularly like the atmospheric characterization stuff. I mean, it's what we call commensal observing in SETI. It used to be called parasitic observing, but that implies that SETI is like, I don't know, sapping the blood out of the rest of astronomy. The term is commensal, meaning that we're not, neither side is hurting the other. We're using the same resources. And so I think it's mostly going to track the rest of astronomy. Resources like LSST, the James Webb Space Telescope, the SKA. I mean, all of the big things we're excited about, multi-messenger astronomy, all the stuff we're excited about in astronomy and astrobiology, I think can be used for SETI. And until we have a better way to know which technosignatures are most likely, I think that by leaning on those, we've got the low-hanging fruit to chase. So I'm just going to say, I'm going to point at astrobiology and say what they said.
But I think the issue there, right, is that if you tie technosignature searches to the evolution of optical telescopes, right, then you are speaking about doubling the capacities every 15 to 25 years. Whereas if you really can benefit from a Moore's law type growth, like you mentioned with as Jill's argument for the Allen Telescope Array, then maybe there's obviously much faster potential for growth.
Yeah.
So I'm wondering whether maybe emphasizing yet underexplored areas like the ultra short pulses, for example, that may not require very large telescopes, but different detector technology may allow a faster growth in terms of exploring the parameter space.
Yeah, I'm really excited about the time domain, the way that that's accelerated so quickly, especially with LSST and then all of the big data. We can keep more data and analyze it archivally now, which is great.
I think Jill has a point, and if once Jill has that, and also Lucian, then we can move on to the next.
Rubin Observatory, the LSST by the Rubin Observatory.
Right.
Thank you.
Right. Jill, do you want to quickly make a point?
Yeah, I think that we need to get creative in thinking about the next generation of telescopes at any frequency and how we can use them commensally. Because I think that actually is probably a better route than looking at archival data where you're going to have these ambiguities you can't follow up. And so if we think about how we can use, we're opening up new dimensions of the observational phase space. And if we think about how we can make use of what other disciplines are building to do a search for engineered signals, then I think we have a great opportunity. So commensal, yes.
All right, I would say we should probably move on now. So our next speaker is will be Bruce Macintosh, high contrast imaging searches for bio and technosignatures. So Bruce, go ahead, please take the.
Find all my Zoom buttons. Hopefully I'm audible now and actually sharing slides. And let me get started. Okay, so thank you very much for the invitation. This is something I've just been starting to think about over the last couple of years, the use of coronagraphs and high contrast imagers for SETI-related purposes, but the use of coronagraphs and high contrast imagers for studying exoplanets is something I've, of course, been working on most of my career. So won't go through the outline because it's a short talk, but I first want to just remind the broad audience about the ways we will characterize habitable planets over the next couple of decades. This is laid out very nicely in the Exoplanet Science Strategy report from the committee that Dave Charbonneau and Scott Gotti chaired. And basically, there's 2 or 3 pieces of parameter space. And a lot of discussion on biosignatures, even in the talks we just heard, has focused it on what we can do now and in the near term, which is JWST and transits. But we should remember that that's a bit of the looking for your keys under the streetlight situation. JWST, though extraordinarily powerful, can really only characterize habitable planets around M stars, and probably around a relatively small sample of those that happen to line up to transit, that happen to be photometrically stable, that happen to be low mass, etc. And so in a sort of phase space diagram of stellar mass, distance from the star, with the habitable zone being this fuzzy rainbow, transit techniques like JWST at infrared wavelengths are characterizing the lowest mass, the habitable zones around lowest mass stars. Imaging, on the other hand, with extremely large telescopes on the ground or future space coronagraphs, is really the future space coronagraphs in particular are the only path we have to characterizing Earth-like planets around sun-like stars. It's essentially impossible to do with transits and impossible to do with ground-based techniques. So they're nicely complementary to each other. If you want to be looking for these technosignatures Jason was discussing around on planets orbiting sun-like stars, that's going to be something we do with coronagraphs, not with JWST. And then a second introductory material thing, just a order of magnitude calculation, which Jason alluded to, a version of 2 for why are these good tools to look for technosignatures. The scale of signals you're looking for is sort of interestingly comparable. So if you're shooting a laser beam at somebody, it comes out in a diffraction limited beam whose angular width is your wavelength over the diameter of your launch telescope. The solid angle of that beam then is that angular diameter squared. And if you have a 1 micron beam and a 10-meter telescope sitting up in space, stuff we could imagine building now, your beam comes out at 10 to the minus 14 steradians. Meanwhile, if you're the Earth, you're radiating your power over 4 pi steradians, which is 10 steradians for my purposes. And so the launch telescope concentrates the emission from a light source by a factor of 10 to the 15, which by an interesting coincidence is the ratio of brightness between a 10-watt laser and the total brightness of the entire Earth. So as Jason alluded to, lasers launched through telescopes can be really bright, and a 10-watt laser launched by a 10-meter telescope is as bright as the entire Earth when seen from outside. Hence, telescopes we built that are capable of seeing Earth through direct imaging will also be capable of seeing very faint technosignals. I assume that's just background noise. And should I be taking questions in line? My Zoom isn't really well set up for that.
No, wait until the end.
Okay. I'll show versions of these figures a couple of times also. This is a what we're trying to do thing showing contrast, the ratio of brightness between a planet and its star versus angular separation and our solar system. I'm going to skip this slide, but with, say, the Hubble Space Telescope, for example, the contrast we can see things at right now is up around 10 to the minus 4 to 10 to the minus 5, enormously far away from any of the planets in our solar system. And that's set by a mix of wavefront errors, which sets this horizontal floor, whether they're wavefront errors from polishing marks on the telescope primary mirror or atmospheric turbulence for a ground-based telescope, and then inner working angle, which sets the smallest angle you can see at, which is set by the diffraction limit lambda over diameter of the telescope with some scaling factor. So the first direct imaging I want to talk about are what we do now on the ground with instruments like the Gemini Planet Imager on the Gemini Observatory. Downside, they're on the ground. On the plus side, because they're on the ground, we can put fancy technology on them and operate on quite large telescopes. And in this phase space, GPI sensitivity is kind of here, 10 to the minus 6 sources at arcsecond-like scales. A long way from our solar system. What it's allowed us to observe are young planets, planets that are much brighter because they're 30 million years old and they're still radiating away their Kelvin-Helmholtz energy. And GPI has, as an example, lots of other groups have done this, has imaged 6 such young planets, masses ranging from, say, 2 to 13 Jupiter masses, as well as a plethora of brown dwarfs and objects like that. That slide shouldn't still be there. There we go. So one question we asked ourselves, where I sort of started on this, was, all right, I can see a faint thing next to a bright thing. Lasers are faint things next to a bright things. What kind of laser could I see with GPI? So Christina Vides, who's now a graduate student at UC Irvine, did some order of magnitude calculations simulating what a laser source would look like if imaged with GPI. This is a 24 kilowatt laser at a reasonable angular distance. On the right is a spectrum. GPI is not just an imager, but a spectrograph, and so it can recover spectral information about objects we look at. It could easily tell the difference between a laser and a young planet from its spectrum, as long as it was sufficiently bright, because GPI is not an Earth-seeing instrument. And these are the detection thresholds in watts of power versus separation in AU for wherever the transmitter is located. Around most nearby stars, we're kind of sensitive to 10 or 100 kilowatt class lasers that could exist now, but not extremely faint signals. The dashed lines, on the other hand, are for space coronagraphs, which I'll talk about in a little bit, which do get down to watt class lasers. The next development in this field is going to be the coronagraph on the Nancy Grace Roman telescope, mostly intended to do cosmology and exoplanet demographics through microlensing, but it's going to carry the first high-performance prototype coronagraph into space, primarily as a technology demonstrator, and it could also operate with a star shade that would give it even greater sensitivity. And on this phase-space figure, Roman operates down to almost 10 to the minus 9 at separations within an arc second. It doesn't quite reach Jupiter in our solar system, but on the other hand, there are lots and lots and lots of known extrasolar planets that are brighter than Jupiter and would be within its sensitivity. And it will carry a spectrograph not particularly optimized for this, but capable of detecting chemical elements like methane. And so, as I mentioned, if it were looking at stars that happen to be transmitting laser signals, it would be sensitive at the level of a few watts, which is comparable to the spectroscopic surveys that Jason alluded to. So it's sort of in the same way. We can separate, laser signals are kind of bright, but stars are really bright. We can separate the laser from the star either through spectral information, as people have done with Kakaira spectra, through temporal information by the assumption that the laser signal is pulsed, or through spatially, assuming the laser is not actually on top of the star, which would be a silly place to put a laser. And so coronagraphs add this additional ability to see different laser signals that, say, aren't pulsed or whose wavelength you don't know going in advance. And then in addition to, just for the landscape, there are also proposals for small sat coronagraphs, not intended, of course, for technosignature detection, but with some capability. My two favorites are the 35 centimeter telescope chronograph that Ewan Douglas has proposed, and then a 3-meter mini starshade that myself and Simone D'Amico has proposed. Because they're small, they're mostly sensitive to the outer parts of solar system beyond a few AU. Okay, the next signature you could look for, here's a pop quiz since we have a broad audience. Let me get my chat window up so I can see the answers. If you're seeing our solar system from outside, what would the second brightest thing in our solar system be? Of course, the brightest is the sun. Chris, you're cheating. I was hoping someone who wasn't a world expert in this would answer the question. But yes, the second brightest thing in our solar system after the sun, it's not actually the Oort cloud, because the Oort cloud is so far from the sun, it doesn't scatter a lot of light. It's the zodiacal debris disk. If you're ever somewhere dark, you can see this beautiful band of light rising up from the horizon. If you have a lot of self-confidence, every time I see it, I doubt myself and don't believe I really saw it. It's scattered light from dust produced by comet and asteroid debris, and it's about 10 to the minus 7 of the light of the sun, 100 times brighter than Jupiter, albeit very spread out. We do see this with ground-based telescopes around systems whose debris disks are massive and young. Here's a gallery of images from the Gemini Planet Imager from a paper by Tom Esposito. And of course, that's a natural phenomenon, but there could be artificial phenomenon that operate on that scale. A large-scale constellation of solar power satellites would also reflect and scatter visible light, even if it's not, mostly solar power satellites don't want to scatter visible light. They want to turn it into electricity to run Bitcoin mines or whatever you're doing with it. But even if your system is 90% efficient, still 10% of visible light would get scattered and be visible somewhere else. And so I'll talk about this in terms of a figure of merit that's the fraction of starlight that is scattered by a satellite constellation, assuming the constellation is mature and operational. Also note, though, that as Jason was saying, persistent long-term technosignatures, a decaying constellation of satellites would actually probably be even brighter because collisions would produce large amounts of short-lived but high surface area dust particles. So what could we see with different technologies? Our solar system, as I said, is at about 10 to the minus 7. Current limits on thermal emission from dust or satellite swarms are at about 10 to the minus 5 sigma, lots of ways to define the exact sensitivity limits. GPI is at about 10 to the minus 4. The Roman coronagraph would be at 10 to the minus 6. Our small sats would be at 10 to the, and the small sats also at 10 to the minus 6, and future coronagraphs at 10 to the minus 7. And so that's many orders of magnitude better than the sensitivity you'd need to see a real Dyson swarm that's collecting 1% or so of the starlight. There are caveats. The sensitivity in these instruments is mostly to structures that are at a large separation from the star, which of course is not where you'd put your Dyson swarm, but it's still an interesting sensitivity level. I'm hoping I can go on a few more minutes since I started late and also ended up with way more slides. The next step, so this figure now shows contrast for Earth-like planets around stars of different masses, emphasizing again that transits are really sensitive to Earth-like planets only around the lowest mass stars. The step beyond Roman will be a dedicated high-performance space coronagraph mission that would operate at the sensitivity you need to see Earth-like planets below 10 to the minus 10. And really, that is the only thing that can see Earth-like planets around sun-like stars. There's 2 large-scale missions on the table, as most people know. The HABEX, Habitable Exoplanet Observatory, a 4-meter telescope purpose-built especially for exoplanet high-contrast imaging. And here's a simulation of what it would see looking at a solar system like our own. You can see a Kuiper belt of comets. You can see an inner zodiacal debris disk on the scale where a hypothetical Dyson swarm should be, and you can see a bunch of planets. And then the other proposed mission is the large UV optical IR telescope, LUVOIR, concepts for an 8 or a 15-meter class telescope intended for both high contrast imaging and broad astrophysical science. And here is a simulated spectrum of a mission like LUVOIR looking at an Earth-like planet showing absorption lines from oxygen, water, ozone primarily. Detecting these species is not the same as measuring their abundance, which I'll say something about in a moment. These missions, this is an adaptation of one of Chris's figures that Dimitri Moe and I put in the exoplanet science strategy, just sort of showing that a 4-meter telescope could survey a number on the order of 40 stars with the ability to see Earth-like planets. The larger LUVOIR class missions could survey 100 to 200 stars with the ability to see Earth-like planets around them. Okay, so what could they see in addition to biosignatures? Jason alluded to this as an example. There was a very nice paper on detecting nitrous oxide with LUVOIR with levels compared to the Earth. So the upper curve is 20 times Earth-like abundances of nitrous oxide. This is the change in albedo due to the presence of that nitrous oxide. And this is kind of a typical noise floor. At around the 20 times Earth-like, the signal begins to become detectable. But there are a lot of caveats. These are just calculations as to whether there's a detectable signal, which is very different than looking at a spectra and recovering.
Bruce,
yes?
Another couple of minutes.
Okay, and recovering a quantitative abundance and setting aside the question of whether there are natural processes that could produce it. A lot of work has gone into, as Jason said, for the biosignatures showing that you need really good spectra. It's easy to tell there's oxygen there. It's really hard to measure the fractional oxygen abundance without really good spectra and detailed inversion models. And that hasn't been done for the technosignatures. For the oxygen case, I'd refer you to Kat Feng's paper. And then Jason also spoiled everything else I wanted to see. So there was this beautiful paper by Thomas Beattie on city lighting with the high contrast imaging showing that you could go from sort of 1% urbanized fractions to 10% urbanized fractions around reasonable samples of interesting stars. So let me just stop there. I guess the conclusions in future works. Chronographs, it turns out, really good at seeing faint things next to bright things, which is what we built them for. Technological civilizations are faint and they're next to bright things, so chronographs can help. They're especially useful beyond the innermost parts of solar systems at AU scales and outward. Think future work. So we simulated that GPI could see lasers. We haven't actually tried looking for it in our huge database of data. Most of our targets are too young to be interesting for that, but there are a bunch out there where we might as well run the laser detection algorithms for free if I have a student interested in this. The Dyson swarm thing is a really interesting thing to do real simulations of. What are the polarization signatures? What are the spectral signatures? What phase angles would you be best off looking at, et cetera? And then also, as Jason alluded to, doing the real work for pollutant detection beyond these beautiful initial estimates, but try and see if you could recover an abundance of a polluting species from a spectrum at what confidence level, including effects of clouds, all the things that we've learned mess the heck out of oxygen detection. We should study its ability to do it for atmospheric pollutants. And so I will stop there with apologies for going slightly too long and talking slightly too fast, but that'll give us some time for discussion.
Thank you very much. That was a great talk. Okay, Ravi and Jacob.
Yeah, so we are open for questions now. We have a few minutes.
I'm trying to see if anything in the chat window is really irrelevant. Mostly looks like a side conversation of various sorts, which is fine.
Looks like David Kipping has a question.
Hi, yeah, great talk. So I'm kind of interested if there has ever been an optical METI experiment. I know there's been radio messages that have been sent out, but has anyone actually deliberately or maybe even unintentionally sent out laser signals that could be detectable?
I'm not aware of anybody deliberately doing it, and I don't think unintentionally, because the beams are so narrow. And in fact, even if you're using, we have these powerful laser guide stars that we use as beacons for adaptive optic systems, and people point those near stars, but they never point them exactly at stars. Plus, stars move. And so I think the odds of those beacons being accidentally discovered are relatively slim. And I don't know, though lots of people on this call would know better than I do, whether anybody's ever actually done the math to say, all right, I'm going to point my laser, but I need to point upstream by an arc second at this star. So I'm going to guarantee my laser beam is going to hit this star. I don't know of any examples of that. But we could. You know, I worked at Lawrence Livermore National Labs. We shot a kilowatt laser into the sky for guide star experiments. And you could practically, with the right filter, you could practically have seen that with your naked eye around Alpha Centauri if we had shot it at Alpha Centauri in the right direction. So we have the technology. I don't think anyone's done it. Aki's asking how much light from a laser guide star leaks out. The sodium layer in the Earth's atmosphere is transparent for to the sodium beam, which is why our beams have to be so powerful. So 99.999999999% of the light, not quite, but pretty much all the photons we shoot from our guide star just keep going to infinity, or hit passing satellites or whatever. The opening angle for the guide star beams tends to be about an arc second. We work to make that small because we want to concentrate the power in the sodium layer as much as we can. The Livermore one we used because it was in the middle of a valley, probably had like a 5 arc second opening angle. But most of them try to be smaller. And then you point it away from the target, basically enough that the light from the guide star doesn't get mucked in with the light from other sensors. So usually that would be a few arc seconds, but bigger than your opening angle, because you don't want the guide star on top of the science target. Yeah, it'd be the same interesting calculation for the Apollo lunar laser ranging pulses, except of course they hit the moon. But if they didn't, you know, both of these, you know, are detectable at by someone who knows how to look and is tuned in and is looking at the right time. I think are detectable at tens or hundreds of parsec scales. You know, they're sort of 10-watt class lasers.
Any other questions for Bruce? Jill, I see you're unmuted if you want to ask a question.
Yeah, it's the last bullet point on your last slide, Bruce.
Mm-hmm.
This idea of using solar gravitational lens. I've seen some talks on this topic which say that basically anything you want to look at that is discrete will not stay in the beam of that gravitational lens long enough to do any observations?
Yeah, that's why I had it down there as future work and didn't have a slide. So as you probably know, there's a group at JPL that's been studying, for those other people who don't know though, the sun can act like a giant telescope if you're far enough away from it. Far enough away is about 600 AU, where it produces an image at such high magnification that in principle, you could see the surface of an extrasolar planet and map out its continents. In practice, as Jill says, planets move, and so do spacecraft. And so how long you could stay aligned to do an observation is an open question. And also new models that include things like the oblateness of the sun turn out to complicate it a great deal. So I put it there because people have been thinking about it very seriously as a way to actually see the continents, and then you could watch them as they cut down their forests or something like that. Or do a much better job of seeing city lights, to be less facetious. But as Jill's saying, it's a very TBD whether it works or not, even if you could get a telescope out to 600 AU and knew exactly where to look. So it's one of those, yeah, people are trying to figure out if it works or not. And I wouldn't bet either way myself right now.
Ravi, you have your hand raised.
Just a quick question, Bruce. Just wondering, with the direct imaging missions, LUVAR, HABEX, and all different architectures, and the Origins missions, we have several other missions that would be flagship missions that would be studying different kinds of planets and with different kinds of techniques. Do we have an idea when we would be seeing what the decadal process would be coming out?
I am not allowed to answer that question. So I'm on the decadal steering committee, so I am not allowed to even speculate about answers to any of those questions. So other people might choose to speculate.
Cool. Thank you.
Yeah, I mean, the public statement, last public statement from the chairs was spring, which does not leave a large window. So I believe an update is due from the chairs.
Adam, you have your hand up.
Yes. I just wanted, could you comment more on I really was intrigued by the idea that an aging Clark belt or an aging set of orbital artifacts that if it was dense enough would actually get brighter in time because it was breaking up. Any more thoughts on that? That's an interesting idea.
You know, in general, it's a sort of surface area to mass thing, right? Dust is an incredibly efficient way to scatter light because you get a lot of surface area out of it. And in all these exozodi systems we look at, all the ones I showed beautiful GPI pictures of, are what you're seeing is not most of the mass, it's the dust produced by collisions between planetesimals. The mass is all in 100-kilometer objects. The light is all coming from 1-micron objects. So you don't need a lot of collisions to really spike up the visibility. Another way to think of it is that, you know, the total mass in those systems is kind of moon masses, but they're incredibly bright because collisions are turning them into dust. And so the same process, but somebody would have to model this to see it for real. This is my intuition rather than a calculation I've actually done. But it's the same behavior we see, and it would make sense. The dust doesn't stay, so once collisions produce dust, the dust either spirals into the star or gets blown out of the solar system, depending on the mass. But as long as collisions keep replenishing it, the dust still turns out to be where most of the scattering would come from. So, but that would be a fun thing to do an actual calculation on. And also, what would it look like? Would it look different than natural dust? You know, what would the size distribution of particles be? What would the phase function in the spectrum of ground up titanium or silicon look like as opposed to the dust that we actually see right now? So hopefully that answered.
That was good.
Jeff is sort of alluding to, yeah, I mean, right, there are lots of arguments about the sensitivity range of ground-based telescopes, but my opinion is plausible simulations, even with advanced wavefront control for 30-meter telescopes on the ground, are still 10 to the minus 8 contrast, not 10 to the minus 10. That until you're getting to 100-meter telescopes and to wavefront control algorithms that, you know, I cannot even imagine, and I do this for a living. So I think it's unlikely that will be at 10 to the minus 10 at visible light wavelengths. But you know, there, as Jeff knows, there are people who are more optimistic than me about that. I'm a pessimistic person. Oh, I also just I forgot to mention this on my first slide, but Daniel mentioned something about Moore's law scaling, and yeah, telescopes are bad because they don't grow as according to Moore's law. The contrast we can achieve with imaging, on the other hand, goes up by by 2 orders of magnitude every decade. So this is actually an area where, until we hit some physics limits, which is going to happen when we get to 10 to the minus 11, there actually is a huge amount of potential gain. And that's probably because it's not glass, it's our computers and our deformable mirrors, and like Jeff says, our fancy algorithms. So, all right, I've gone way over, I apologize.
I think are there any, if there's not any other questions, or are there questions? Ravi?
Very quick question. It's not even a question, it's a comment that Russ Belko made in the chat. Maybe we missed it. He says that a gibbous Earth in the Hab zone of the nearest K-star would be above the sensitivity curve of Roman. So we keep thinking mostly about Sun-Earth Hab zone imaging, right? So even the K-star Hab zones with the habitable zone planet and the K-star apparently is going to be above the sensitivity curve for Roman.
Yeah, for one star if you get lucky. So yeah, there's definitely some potential there, but it's a struggle for Roman. But it is a good reminder. And we do tend to think of M stars and sun-like, and poor K stars get neglected. Poor things.
All right, well, it's probably time for a break, and we will come back in 15 minutes, and then we will have the talk from Niki Parenteau. So, okay, everyone, see you soon. All right, so are we ready to go?
Yeah.
All right. All right, welcome everybody. Welcome back. Niki Parenteau, am I pronouncing your name correctly, Niki? I'm sorry if I...
Parenteau, it's kind of a hard one.
Okay. Well, so now we're going to be, digging into biosignatures, which is great for us to be able to have a conversation from strength after this, hopefully. So Niki, please go ahead.
Okay, I'm going to, sorry, just a moment. I'm going to plug in my... Okay, so thank you for asking me to speak today. And I do want to focus on biosignatures, but as I was listening to the talks earlier, and then I also listened to the Technosignatures talk in the Goddard Seek seminar series, I'm going to try to synthesize and find some commonalities between biosignatures and technosignatures. And I've done this on the fly. I've inserted a couple of slides during Jason's talk as I've heard things. So apologies if this comes off a little bit rough, but hopefully we can just have a chat today. Okay, so if you can advance to the next slide. So today what I wanted to provide an overview of our first remotely detectable biosignatures. And in the title, I emphasize the distinction between simple life forms and higher life forms. So by simple, I mean microbial biosignatures, and higher life forms, for me, vegetation is considered a higher life form. So that's why I had a more general term, as well as intelligent life and, technosignatures that we heard a nice summary of in the first talk. And then I thought it would be worthwhile to chat a little bit about in situ biosignatures, which are relevant to life detection on solar system planetary bodies, because ultimately I think that there's a lot of lessons learned that we can share between the three communities. So the in situ biosignatures, the remotely detectable biosignatures, and the technosignatures communities. And then as I was going through the talks in the Seek seminar series, I was struck by a couple of things, and it was a talk that that Jacob Hochmisser gave where he talked about filters. And so in trying to make this talk useful to you all, I thought I would talk about how life evolves within the context of its environment. It's certainly relevant for understanding the evolution of life on Earth, but it also might be useful to think about this in the context of trying to think about the potential for evolution of intelligent life on other planets. And in particular, I want to talk about environmental selective pressures and how common or uncommon they may be across different planetary bodies. And as a case study, I wanted to talk about the evolution of oxygenic photosynthesis. The reason I wanted to focus on this is because so much emphasis is placed on oxygen as a biosignature. And also it's important for the evolution of life on our planet because it set the stage for the evolution of aerobic respiration, which a lot of energy can come from that. And ultimately several steps down the road, I think kind of allowed for the evolution of big brains and intelligent life. And then again, as I mentioned, we'll try to broadly think about the environmental selective pressures for intelligent life. And again, this comes at from the perspective of maybe target selection. And I know that for technosignatures, there are broad surveys that are done, but this is relevant if, you know, observing time is limited and you have to just select a few targets. And then we're going to talk about the detectability of at least some of the microbial and vegetative biosignatures. Next slide. So to start off with, I just wanted to provide a definition of a biosignature. There are several different variations within the literature, but this definition has come about from an activity by the NExSS sister RCN N-fold, which is Network for Life Detection. And this activity is, it's called the Life Detection Knowledge Base. And we had a community workshop for this a few months ago. And the knowledge base is meant to be an online community-owned resource to provide knowledge and support discourse about the detection of signs of life. I think that technosignatures can be hosted in there as well. But through this activity, the community kind of centered on this definition. A biosignature consists of substances, structures, patterns, or processes, or ensembles of these features, so multiple lines of evidence that indicate the current or former presence of life, so extinct or extant life. So going forward with that definition of biosignature, next slide. We'll just do a brief survey of exoplanet biosignatures, and most of these are probably familiar to this group. There can be chemical disequilibrium in the atmosphere, so oxygen, methane, different singular biogenic gases and their byproducts, so oxygen and ozone, N2O, methyl chloride, other things. Also, there's planetary surface features. The red edge of vegetation, it seems that astronomers do focus on that quite a lot. There's polarization due to chiral biomolecules. So there can be an enantiomeric excess, what we call in biomolecules. So there can be an abundance of one-handedness of a molecule over another. That's indicative of life. Also, there's been surveys done of other surface features, so different types of pigments. So Shilda Sarma, who is a microbiologist, has proposed bacterial rhodopsin as a surface biosignature. Eddie Schwederman has a nice paper on carotenoids. Sid Hegda has a really nice survey of a variety of different photosynthetic, not just photosynthetic pigments, but pigments in general. And then also, this shouldn't be under non-photosynthetic, but anoxygenic phototrophs. So very primitive phototrophs have a variety of different photosynthetic pigments that we can look for. Next slide. And this is a figure taken from Eddie Schwederman's paper summarizing sort of the state of the art of exoplanet biosignatures. So if you want one reference to look at, I direct you to this paper. And this was one of the products of the NExSS Exoplanet Biosignatures workshop from 2016. And so in addition to the ones I mentioned, you can look on the right and see temporal biosignatures, so seasonal changes in gases or surface features. Next slide. And Jason covered this a little bit in his talk, but I do want to briefly talk about in situ biosignatures. So ones that are relevant for understanding the origin evolution of life on our planet, and then other planetary bodies within our solar system. So these biosignatures are, you know, especially for solar system bodies, are where you can go and analyze things. These aren't, some of them are remotely detectable, but you really need a rover or a lander or something to go and analyze them. You can bin these in different ways, but these are just some general categories. So microbially influenced sedimentary structures such as stromatolites. So these are sort of community structures that microbes form. Microbial fossils, the image there is taken from these controversial fossils in ancient rocks in Australia. There's a broad class class of chemical fossils. So there can be biominerals. So microbes can actually influence and tightly control the formation of biominerals so that they have a very specific range of size and crystallinity, etc. Below that, you see an image of what's called biologically influenced mineralization. So that just means that through the metabolism of microbes, they can alter their surrounding microenvironment so that it induces mineral precipitation. So an example of that is acid mine drainage. That's what you see there, and that's what the Rio Tinto is in Spain. Biogenic gases, you're pretty familiar with those. Also organic compounds such as lipid biomarkers. So we know that we have, for example, cholesterol in our body. Well, it turns out that that compound survives for billions or at least a million years in the rock record. The bacterial version of that, a hopane, can survive for 1 billion years as well. And then there's, of course, stable isotopic fractionation. So next slide. And as Sean has alluded to earlier today, there's a class of biosignatures, sort of a novel approach, agnostic biosignatures, and Sarah Johnson has really been pioneering this. And so it's trying to avoid the bias of Earth-based life. So a couple of different examples are chemical complexity. Can we just generically analyze the complexity of different compounds and infer its biogenicity? And you can do that by doing mass spec measurements. Also nucleic acid binding. Another way to think about it is instead of looking, for example, DNA on another planetary body, DNA is a highly Earth-specific invention. Instead of that, you can just say, I'm looking for an information-bearing polymer, so to be a little more general and agnostic about it. And then also, as Sean mentioned, I think Tessa Fisher is here with us today. So Sarah Walker has really pioneered, detecting unknown biology on unknown worlds with a Bayesian framework. And my understanding is that Tessa might be applying that to technosignatures, which is fabulous. And also I saw in the chat, we might ask the question, what are some agnostic technosignatures? So I think that Catherine Denning mentioned waste heat. So that can be an agnostic biosignature, technosignature. Next slide. And I wanted to point out that different communities look for different things. So for example, on the early Earth and Mars, the focus has really been on looking for extinct life, so preserved organic molecules. There is a possibility of extant life on Mars deep in the subsurface. So for something like that, you might be looking for methane, and you probably are aware of the controversy of methane on Mars. For ocean worlds, you're tending to look for extant life, so something that's erupted from that subsurface ocean. And the community tends to look for more simple building blocks of life. So things like amino acids, carboxylic acids that can make membranes, different cellular structures, etc. For exoplanets, you're primarily looking at extant life. So, life is out there making gaseous products and also the surface photosynthetic pigments. Next slide. So going back to the exoplanet biosignatures, I wanted to kind of explore the emphasis that astronomers have placed on atmospheric oxygen in the vegetation red edge. So what you're looking at there is called Earth's biogeologic clock. It was created by Dave DeMarais. And what it shows is on the face of the clock, you can see the origin of the Earth. And then you can see the origin and evolution of life as you go around that clock. So the point that I generally want to make with this is that microbes have dominated at least our Earth for nearly 4/5 of its history. And as you go around the clock, just for a couple of seconds before midnight, you have intelligent life for humans. Now, in listening to the earlier talks, I understand that life, the intelligent lifespan, may be extended by a few hundred millions of years. But, and I have to say my perception now is being challenged and changed, which is great. I would have originally said, oh, you're going to find microbial biosignatures before you find any technosignatures. But as I've listened to the talks, I think that it's possible that technosignatures could also dominate a planet, and also they could simultaneously exist with very simple microbial biosignatures, because we still have an oxygenated atmosphere today, which ultimately came from cyanobacteria. So again, plotting this. So as you go around, I mentioned the evolution of cyanobacteria and oxygenic photosynthesis, and the great oxidation event happened about 2.4 billion years ago. If you continue around the vegetation red edge, now vegetation has only been around for about 400 million years. So again, when you think about other biosignatures to look for life, there's a big chunk of time that's not necessarily covered. So next slide. And also I wanted to make the point that Noah Planovsky has shown that oxygen may have been at very low, likely undetectable levels until 0.8 billion years ago. So again, if you just look at that geologic clock, how are you going to recognize life for the bulk of Earth's history? Next slide. So that's where the question marks come in. So I wanted to explore a little bit some knowledge gaps that still exist for biosignature research. One of which is, characterizing different types and biosignatures, both gaseous and also surface. So I've been focusing on more primitive anoxygenic phototrophs, which could have dominated the planet obviously before the rise of oxygenic photosynthesis. They don't produce any gaseous products, so we have to look at surface features of those. Next slide. And as the point that I made earlier, that I didn't have time to remake this geologic clock image, but you could extend that length of time over which intelligent life could have dominated the planet. And my understanding is that this might be what's considered the class 5 planet, where intelligent life dominates. Next slide. As I mentioned, we're focusing on the biosignature knowledge gaps. Next slide. So there has been a lot of recent work being done just cataloging different surface features of pigments. And so what you're seeing on the right are different cultures of anoxygenic phototrophs. And these are representatives from all the major groups of anoxygenic phototrophs. And what I'm doing is I'm measuring the reflectance spectra. These pigments absorb in the near infrared. They don't absorb in the visible range of wavelengths. Next slide. That actually makes them well suited for living on M-dwarf exoplanets that emit primarily in the near infrared. As I'm going to be addressing later, it might be tough for oxygenic photosynthesis to get enough photons in the visible range of wavelengths to live on those types of planets. So again, anoxygenic phototrophs, if you look at the plots, so the different colored pigment spectra, down on the bottom, they absorb clear out to 1080 nanometers. So right sort of at the maximal photon flux of, for example, 80 Leo. Next slide. This is just an example of, so I mentioned that we measured the reflectance spectra of pure cultures, but I am actually a field-based microbiologist, microbial ecologist. So I like to go out in the field and see how things are really growing. And, and to really get at this issue of detectability, which I'll talk about later, are these things really growing in high concentration? Are we realistically going to be able to see them on our planet, much less an exoplanet? So again, I do a lot of field work. That's in the upper right-hand corner. You can see a pool of purple bacteria, and I'm measuring the reflectance spectra of that. And what you're seeing in the plot here in the black is the reflectance spectrum. And then below it in purple is the absorption spectrum of the pigments. And there are some, the title said BCLJ. That means bacterial chlorophyll. They absorb in the near infrared. And where the pigments absorb, they equate to dips in the reflectance spectrum. So beyond the kind of very simple vegetative red edge, the edges of these other primitive phototrophs have lots of other features. Now, these may not be detectable by even LUVOIR through direct imaging because the resolution needed is quite fine. But I and others are still cataloging these. Next slide. Another type of biosignature that I'm exploring are ecosystem signatures and also community signatures. So a couple of points to make here. I know that we might not have this resolution from LUVOIR, but if you could distinguish like, a little bit of continental landmass on an exoplanet from an aqueous ocean, there might be different types of signatures in those places. And also the thing to remember is that, you know, these microbes aren't going to be growing in pure cultures on an exoplanet. They are likely going to be growing in communities. So what does a community signature look like? I haven't published this yet, but I need to get around writing it up. So also what you're seeing is a layered microbial mat. And so these are very complex signatures that come from how light is reflected and bounced around in these mats. Next slide. So to back up a little bit, I wanted to talk about how life evolves within the context of its environment. And again, I was influenced by the talk that Jacob gave where he was talking about great filters. So there's been a lot of work done, obviously, on major evolutionary transitions, but I wanted to focus again on the evolution of oxygenic photosynthesis because oxygen is so important and has set the stage for again, evolution of aerobic respiration, but maybe even Cambrian explosion, etc. So if you go to the next slide. So a couple of broad statements about the evolution of photosynthesis. You may have seen in the literature, oops, can you go back one? Yeah, that one. There, thank you. You may have seen in the literature that people argue for the evolution of photosynthesis to have arisen in specific types of microbes, specific types of anoxygenic phototrophs. It is really hard to pin it to any one microbe. So be cautious about that if you're reading about that. If you go to the next slide, the way that we should think about evolution of photosynthesis, and this has been driven home and conceived of by Bob Blankenship, who's an expert on this, it's useful to consider photosynthesis as a mosaic of traits, each one of which has had a separate evolutionary history. So you can see photosynthetic pigments is one group that has a separate evolutionary history, what are called reaction centers. I won't go into detail, but it's sort of the business end of light absorption and charge separation. The antenna pigments have had a different evolutionary history, the electron transport pathways, and the carbon fixation pathways. So you can look at any one subsystem and come up with, quite frankly, whatever evolutionary scenario you want. Today, we're just going to focus on reaction centers because it's sort of the business end of the stick. If you go to the next slide. Just a review very briefly on what oxygenic photosynthesis is. You're probably very familiar with the equation down at the bottom. It shows carbon dioxide and water getting converted into sugar and oxygen. But the way that I tend to focus on this is I look at what's the electron donor. So the way that photosynthesis works, it's extracting electrons from water and it's generating oxygen as a waste product. Separately from that, carbon dioxide is fixed into sugar or CH2O, formaldehyde. And in talking with Origins of Life chemists in our exobiology branch, I just wanted to make this point. Even when you're thinking creatively about life on other planets, always keep in mind that life needs to maintain an intermediate redox state. So even if you're thinking about life on a highly reducing planet, maybe you're trying to use methane as your carbon source, you always need to get to CH2O because then you can make stuff. You can't make a lot of stuff from methane. Next slide. So this is really talking about the evolution of the ability to extract electrons from water. I know this is a busy slide. I'm not going to go into great detail, but this is where the environmental context comes in and the environmental selective pressures come in. If you focus on the very top, there's a redox scale up there, and I plotted on that scale the redox potential of hydrogen, iron, and water. And then I've shown a little volcano. So on the early Earth, it's thought that volcanoes, emitted a lot of volcanogenic reductants. So things such as hydrogen, hydrogen sulfide. That's easy for life to eat. It's easy to extract electrons from them, but those were thought to be limiting. So then that sets up this environmental selective pressure to be able to use higher and higher redox potential electron donors, ultimately leading to water. But it's actually a big jump to go from hydrogen all the way up to water, and it requires a lot of innovation. So I just want to make the point that oxygenic photosynthesis is complex, and we should not necessarily assume that it's going to evolve on exoplanets. And I just urge a bit of caution here because so much emphasis is placed on oxygen as a biosignature. I'll just briefly describe what you're seeing in the bottom panel. So on the left, these are diagrams of reaction centers. I just want to make the point on the left that anoxygenic phototrophs use single reaction centers. They're relatively simple. There had to be some sort of evolutionary transition before you get to oxygenic cyanobacteria, which have two linked photosystems and also the ability to extract electrons from water. That's a big evolutionary jump. A lot of people focus on trying to understand what happened here. So our group and others have looked at intermediate reductants such as iron. And again, this is where the environmental context comes in. If you go to the next slide. So there's Archean ferruginous oceans. So there was lots of iron around. So that could have provided a transitional electron donor. Next slide. We know that the oceans were ferruginous because we have vast deposits of iron formations today that are economically mined in Australia, and they were laid down at various points throughout the Earth's history. Next slide. So the work that we do and others do, you can, again, hypothesize these sort of evolutionary missing link organisms, and then you can go to modern environments, modern what we call refugia, that may still host them or host the metabolic capability to do that. So if you go to the next slide, and again, I'm not going to go into detail here, but this is just a modern system. It's a hot spring in Yellowstone. It's an iron spring. It has a lot of reduced iron coming out, and there are cyanobacteria growing there. So we've done a lot of work trying to look at can cyanobacteria grow anoxygenically using iron. But again, the basic point is that you hypothesize that this evolutionary transitionary form existed, and then you look for modern representatives. Next slide. So now to speculate about the evolution of oxygenic photosynthesis on an exoplanet. So again, we need to think about the selective pressures. So one of which are the stellar properties. So we need to think about the light available at the surface of the planet. And a lot of folks have thought about these atmospheric windows and how it may have driven the evolution of pigments absorption. And it's a nice story that holds up potentially for chlorophyll A, which absorbs in the red. And it's actually positioned at the maximum photon flux at the surface of the planet from our star. However, that does not hold up for pigments from anoxygenic phototrophs because some of them sit right under those water bands. And so also a point I want to make is that phototrophs are getting plenty of light. In fact, even oxygenic phototrophs in vegetation, they only absorb like a few % of the incoming solar flux. So in fact, they get photoinhibited. So I think that we need to be cautious about thinking the evolution of pigments and photosynthesis is driven by these atmospheric windows. There's likely other factors at play. Next slide. So as biologists and planetary scientists, you know, we think about certainly water as a requirement for habitability, but there's other things that we look at as well. Raw materials, you know, the carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. I really like the work that Hilary Hartnett and her group are doing, looking at the signatures potentially related to the use of those other raw materials. We can also look at electrons and other energy sources, so as well as light and different, again, stellar energy sources. So again, moving beyond just looking for evidence of liquid water on the surface, we can look for and ask the question, do exoplanets host these other necessary ingredients for life? And we can also think about what we call clement conditions. So what's the range of temperature and pH, et cetera, certainly over which life as we know it exists on Earth, but we can speculate a little bit about the limits of life on other planetary bodies. If you go to the next slide. So one thing that I've been doing as a microbiologist, again, trying to understand sort of the setup for evolution of life on Earth, but the potential, like, is this common within our solar system and beyond. So I want to focus on volcanism in general because it's a really nice source of reductance. So I've been trying to pay a little bit of attention. And again, this is completely outside my wheelhouse. So I apologize if I get it wrong, and please correct me because I like to learn. So I've been looking at the work that's being done on the coupled climate tectonic models to address life potential. So the mantle convection and surface tectonics and availability of reductance. So folks may look at that and, I think the work is done to try to see how it influences the evolution of the atmosphere. I tend to look at it and say, okay, what's there for the microbes to eat? So the volcanic degassing, again, can provide a source of electrons for phototrophs as well as chemotrophs. Next slide. So moving into detectability. So I tend to be actually a little bit more conservative here and realistic. And I'll talk about that in terms of detectability of these, in particular, surface features on other planetary bodies. And then also, you've probably heard a lot about putting these biosignatures and ultimately technosignatures within a false positive and false negative framework. Next slide. So when we think about detectability of biosignatures, we have to think about everything that happens to that biosignature from the moment it's formed to the potential transformations that happen before it reaches a potential observer. So whether that's an in situ instrument or a telescope looking at an exoplanet. So we tend to, this kind of comes from looking at in situ biosignatures on early Earth, as well as ones more relevant to Mars. So we look at the diagenetic alteration of biosignatures, and that just means anything that attenuates that signal. So there is a biological diagenetic window that these things have to go through. And I will point out that microbes and other things are pretty efficient at munching and destroying these. And there's also a geologic diagenetic window. So things can be destroyed, again, a little bit more particular to the in situ ones, by burial and heating and so forth. More relevant to exoplanets and the gaseous ones are photochemical processing and destruction and potential formation of secondary biosignatures such as ethane. And I think that was Sean Domingo Goldman's work. So in this cartoon here, you can see down at the bottom, the marine biosphere. So that's extant life. It's producing things, but also it's getting destroyed. And the UCR team has done a great job looking at the biogeochemical cycling within that system so that we can understand what the net flux of the gaseous compounds would be from the surface, then that would go into being photochemically processed. So if you go into the next slide. So this is just to show the complexity of biogeochemical cycling that can happen. And I know the exoplanet community has that. I've seen the slide where you say planets are hard, and it's an exceedingly complex diagram. This is what we call our awful diagram. It's also complex, but what it's showing is a layered microbial mat. And in the green boxes are different classes or groups of bacteria. You can just think of them as different types of metabolisms. You can try to be a little more general and agnostic about it. The point is that the products made from one sometimes are rapidly consumed by another. So there's fast and tightly held biogeochemical cycling. I know that the community is mostly interested in the flux off the surface, but again, there can be a lot of limitation, a lot of destruction that goes on within the mat. You can just extend this in a water column of a lake or an ocean as well. Next slide. So moving into the surface biosignatures, I just wanted to make a couple points about detectability here. There is this beautiful cartoon of this purple Earth, and I know a lot of people have been thinking about Archean purple Earth and looking at its detectability. And there's just one example of a paper there. But if you look at how covered that planet is, and because I'm somebody who works in the field, I don't necessarily think that we would expect to find a planet with that much coverage, which would really pump up the signal and really make it detectable. If you go to the next slide. So I think that for the modeling of the disk average spectra, if we can just get a little bit more realistic, like cell densities and coverages, it would be interesting to see and ask the hard question, you know, are these surface features going to be detectable? And the answer may be that they're not, and that's okay. It just helps us select appropriate targets to look at. Just to show you a couple of examples of what these things look like in the field, the image on the left there, you can kind of see this faint coating of purple sulfur bacteria growing on top of the sand. So this is a marine intertidal area. It's called Sipowis Salt Marsh near Cape Cod, Massachusetts. And this is Lupita Tovar, a student that I took out in the field. And we were measuring the reflectance spectra of these purple bacteria and other communities growing within the sand. Again, you can see that the cell coverage is not that great, and consequently, the reflectance spectra were not that strong. So again, when you move away from that really dense pure culture work and getting out in the environment, it's kind of a more sobering story. Also, I'm a little concerned about planktonic suspensions in lakes and also in the marine system in the open ocean. This is Green Lake in New York. There are plates of purple bacteria that grow in the water column there. And so we took a boat and rowed out on it and just measured the reflectance spectra on the surface of the water to see if we could detect that pigment signature, which is about 15 to 20 meters below the surface. And the answer was that we couldn't. And it's because that that reflectance signature was sort of attenuated probably by the specular reflectance of the water. And I have a kind of an ongoing joke with my colleague, Nancy Kiang, who does a lot of modeling. She's like, well, why don't you just model that? And I said, well, I like to go out and measure it. And I think that these field measurements can provide an anchor for the modeling that's done. Next slide. I also wanted to make a couple of notes about extremophiles. I see astronomers kind of focusing on extremophiles and speculating that that type of life could dominate an exoplanet. And I wanted to make the point that the type of life you're most likely to see are ones that grow in more benign conditions that aren't constrained by these environmental extremes. I say that because, again, having done field work for almost 25 years now, when you go out in these environments, sometimes there's not very much biomass out there, even in the presence of abundant energy sources. So again, I tend to work in volcanic systems, hydrothermal systems. There is a great flux of electrons, great flux of hydrogen and all sorts of things for these microbes to eat. You would think that there would just be abundant biomass. Again, that's not always the case. So the thing to keep in mind is that there can be other factors that control the distribution of these microbes, and they're contending with these extreme conditions, and they have to expend a lot of energy dealing with that high temperature or dealing with that very acidic pH. So again, I just want to make the point that don't necessarily think that extremophiles are going to cover another planet. The next slide. Again, I threw this slide in after hearing Jason's initial talk, and I thought it was kind of interesting to hear the thoughts on the spread of technosignatures, and they could certainly spread beyond sort of the planet of origin. And I was thinking about that, and even though I just said extremophiles may be out there, they may not be detectable, I do want to make the point that microbes can colonize so many different habitats and can eat so many different things. You know, they can, again, eat gases, they can extract electrons from rock, again, inhabit a wide variety of environments. You may not ever see them, but they could actually colonize a huge number of different types of environments on exoplanets out there. So it gets into this false negative issue, which I'll say a little bit more about. Next slide. So again, talking about the false positive and false negative framework, I will say that the exoplanet community has really been driving this, has done an excellent job. And Vicki Meadows led a paper on considering the false positive and false negative framework for oxygen. So I definitely refer you to that paper, and she goes through all the different scenarios by which oxygen could be abiotically produced, so false positive. For me as a microbiologist, I'm more fascinated by the issue of false negatives. So life is out there, but we may never see it. Next slide. So I want to point out a paper by Owen Lemur, where he was looking at and asking the question, could a photosynthetic biosphere survive on an M-dwarf exoplanet? Does it get enough photon flux in the visible range of wavelengths? And could you ever detect oxygen as a biosignature on these types of planets? So I won't go into detail here. I know time is getting short, but his conclusion was that to a first order approximation, an Earth-like biosphere would be potentially light limited around the coolest of stars, regardless of the wavelength limit for oxygenic photosynthesis. So even if you pushed oxygenic photosynthesis further out and allowed it to absorb in the near infrared, they would still be light limited on these N-dwarf exoplanets, and they might produce a little bit of oxygen, but again, you may never see it, you may never detect it. And that's something to keep in mind, you know, when we think about targets for, well, I guess the JWST observing campaigns have already been selected, but as we think about other targets for LUVOIR and whatnot, just be careful which planet you want to observe. Next slide. And also, Chris Reinhardt has done a really wonderful job looking at false negatives over the course of our history on our planet. So again, oxygen may be produced on the early Earth, but you may never see it. Next slide. So I think that, I think I alluded to this at the beginning of the talk. I think that there can be a lot of sharing of lessons learned between the in situ biosignature community and the remotely detectable biosignature community and the technosignature community. You can look at examples from the early Earth, the controversy surrounding determining the biogenicity of microfossils and all the arguments that came out of that. And one take-home message is that you need multiple lines of evidence. Same thing with ALH 84001. You know, there were a lot of individual lines of evidence that each could have been discounted for looking at those putative microbial signatures in that meteorite, but taken together, the authors suggested, well, you know, this might be suggestive of life. So those examples are worthwhile considering. And then of course, Viking, where you just went directly and looked for evidence of life without considering the habitability first. So again, kind of the lessons learned, you want to characterize the habitability of an environment first. Obviously for exoplanets, you're very attuned to that and looking at availability of liquid water. The Mars community has done an excellent job of that as well, but also considering more parameters. So I know, for example, Tom Bristow now with all the data coming from the Chemin instrument on the Curiosity rover is looking at energy sources for microbes. So we know that there was evidence of liquid water in the past, but can you look at other components from that habitability diagram? Another thing that came out of all these lessons learned, again, multiple lines of evidence. For in situ biosignatures, you can read Danny Glavin's recent paper looking at amino acids and their chiral asymmetry. That may not be enough. So in addition to that, you may need to look at their isotopic composition. For exoplanets, you probably don't want to depend on any singular biosignature. You want to look at, if you have that capability like with LUVOIR, you can look for oxygen plus a photosynthetic pigment edge. Doesn't necessarily have to be a red edge. Again, these pigments can absorb in a variety of places. We're still understanding the environmental drivers for that. So we're just going to call it a pigment edge. So again, as I mentioned, we want to bring together these communities. And I think that, you know, webinars like this are the first step for that. So this has been really great and I'm learning a lot. But also I want to point out the joint NFold and NExSS workshop that's coming up. It's Standards of Evidence for Life Detection. It's July 19th through the 22nd. And there we're really trying to bring together the in situ community and the remotely detectable biosignature community and ask what are again, the standards of evidence that we need to come up with a, you know, an announcement of life, or can we statistical constraints on that. So there's the link if you want to sign up for that. Next slide.
Niki, a couple more minutes.
Yeah, I'm just wrapping up. Thank you.
Well done.
So we've covered quite a few things in this talk, and hopefully some of it's been useful. Again, I tried to synthesize on the fly as I learned more about the technosignatures, and I think that certainly more needs to be done in this area in terms of synthesis and looking at commonalities. So we just briefly reviewed the remotely detectable biosignatures. There are quite a few knowledge gaps out there, so there's still work to be done, and I think that other biologists can join that community, weigh in, and characterize other types of biosignatures. We talked about an example of how life evolves within the context of an environment. So understanding, again, the general set of environmental selective pressures that are set up for evolution of life on Earth and trying to think broadly, are these a common set of features on other planets? And could it, again, ultimately set up for the evolution of intelligent life on exoplanets? We talked a little bit about detectability. I just kind of urged some caution there. Again, from my bias, you can take it with a grain of salt as a microbiologist. And then again, let's all work together. Let's bring all these communities together. And with that, I'll stop and take any questions that you might have.
Thank you. That was great. That was really fascinating. Okay, so Ravi and Jacob.
Yeah, the floor is now open for questions. Jason has his hand up.
Yeah, I'm really interested in the slides you had before about the workshop on getting the in situ and remote communities together to think about false detections and standards for detection. This is obviously a big problem in Technosignatures as well. And so I'm curious where you think those interfaces can best happen.
Well, so right now, so I and probably others who are joining us today are on the SOC for that. So what we're going to do is come in sort of with a straw man version of what those standards of evidence might be, and then ask for community input and see that if we can't arrive at an agreement that works for both in situ biosignatures and technosignatures and the remotely detectable biosignatures. So it's a work in progress. We're looking at, again, these examples of what we've already been through. So ALH 84001, also the recent example from phosphine, the putative detection of phosphine as a biosignature in the clouds of Venus and how that played out.
Okay, so, but I'm curious how we can connect to technosignatures. Do you think this is something that should be part of that discussion, or is there going to something come out of that workshop that we should then work? Because they seem like related questions, but different applications. And of course, people in SETI, have had their experiences with things like those examples as well.
Yeah. So, please join us and bring your experience. But again, regardless if it's a biosignature or technosignature, you're still going to have to address false positives and false negatives.
Right.
And so that is a major foundation of this. But also, and this isn't my wheelhouse, this is, you've heard other people talk about it, but assigning confidence levels to the detection. So that's part of that discussion as well. And you probably have addressed that in the technosignature community.
Yeah. One place that we've connected to other groups thinking about this problem, since we're looking for technology, this is one place a connection with anthropology has helped. When they find artifacts and they want to distinguish them from geofacts, they have to think about how they say this piece of rock is an artifact, it's not just a geofact. And so I think this problem of false positives, obviously extends beyond biosignatures and technosignatures as well. And so I found it very fruitful to reach out and find other communities where, they have like whole journals on this and so on. But that's really neat. I'm looking forward to that.
Yeah, thank you for pointing that out. In addition, we're actually looking into the medical literature as well. They deal with that as well. Thank you.
Adam?
Yes, thank you. That was a lovely talk. One thing, you referenced the different types of planet. So when we were doing that work, what I was specifically thinking of was in the different, type 1 planet had just no atmosphere, nothing was going on. Type 3 and type 4 were what we called a thin and thick biosphere. And by thin, we meant that the geophysical system, the geochemical physical systems had not really been strongly modified by life. And so I guess what I'm wondering is, so obviously at type 4 was, oxygen was the example, but can you think of other ways in which you could get strong modification of the systems, of the other coupled planetary systems that wouldn't involve oxygen?
Yeah, so like the thin biosphere. So I primarily work with phototrophs. And so there are folks out there that work with methanogens and so forth that could really focus on the chemotrophs, the influence of that. And there has been a lot of work in looking at, all the complexities of methane as a biosignature on the Archean Earth. in terms of the phototrophs, it was initially thought that there may not have been very much productivity on the early Earth, obviously compared to oxygenic photosynthesis. So they could have influenced, again, surface signatures, not necessarily gaseous, because they don't make gaseous products. So I was a little conservative about that. However, I saw that, I think it was Josh Kersensen-Totten and David Catling and others had a paper recently coming out looking at carbon cycling on the early Earth. And so I think kind of one of the upshots is they suggested that there actually was a fair amount of productivity on the Archean Earth. So suggesting that, again, both chemotrophs and phototrophs were quite active on the early Earth and may have then subsequently influenced the environment more than we previously thought.
Yeah, I've seen estimates of the net primary productivity for the Archean of being 5% of, which is, you know, smaller, but it's not so small. I mean, it's not 100,000th of a percent. So, I mean, I would imagine that there could be surface features if, or, you know, or changes in ocean reflectivity or other things. I mean, the problem for the early Earth is that there wasn't a whole lot of land, unfortunately. It was mostly ocean, at least according to some people. But still, 5% is still, you know, that's a fair amount of net primary productivity.
Yeah, and that's why I wanted to kind of focus on what's the, you know, how reliably could we detect microbial life in not just the open ocean, but again, marine intertidal areas. So I understand that there wasn't much continental landmass, but there were large, like we know from evidence in the rock record, there are stromatolitic reef systems in shallow nearshore areas. But, you know, would that be detectable on an exoplanet? You know, there's still a lot of work that needs to be done there.
Thank you.
Vlad.
Yes, hello, Niki. Thanks for a very informative talk. And so I was thinking about it, and the question that I have is, for the first 1.5 billion years, our Earth didn't have, didn't employ the oxygenic photosynthesis, right? It was a boring billion, actually. So the question is that, what do you think, whether it's a freak of the oxygenic photosynthesis is a freak of nature, of biology, or it's a law of biology? So because, you know, we are now emphasizing the search for oxygen, but before we do that, we need to understand, right, whether it's the next evolutionary step that has to happen, whether it's one of the many different pathways.
Yeah, thank you for asking that. So again, that's why I was trying to, so if you're asking my opinion, I worry that the evolution of oxygenic photosynthesis is not necessarily inevitable. Again, it's a very complex process. It takes a lot of invention of complex cellular machinery to come together. That's why I was trying to back up and look at, again, what was the environmental scenario that set up, like what were, again, the driving factors that set up that to happen on the early Earth. So again, it's focusing on the availability of volcanogenic reductants. They were limiting, it forced life to invent a way to extract electrons from water, which is widely available. That's why oxygenic photosynthesis is so prevalent on the Earth, because, and they kind of code everything actually, or they're difficult for me to deal with because I'm trying to find the anoxygenic phototrophs. So it may not be inevitable. If we can characterize exoplanets and understand sort of their interior evolution, again, if you can do that, that might help you then target which exoplanets to look at that might hold a higher chance of having evolved oxygenic photosynthesis. So it's just something that I've, you know, it's probably an incomplete thought that I've had, but again, I'm trying to think of the broad environmental drivers.
Thank you.
Bruce.
I'm just sort of prompted by that to have a couple of thoughts on you know, whether we're overemphasizing oxygen. I don't think we are in the mission design. It's used as a use case to assess signal to noise ratios for something like Habex or LUVOIR, but basically Habex or LUVOIR look at every wavelength you possibly can with a mission you can plausibly build at an SNR that's as good as you can plausibly get, et cetera, et cetera. So we wouldn't, even if somebody told me today there's no oxygen out there, I wouldn't change the design of any of these missions. They've got good spectrographs that can look at a broad range of wavelengths. We may learn different things when we look at them. And of course, as most people know, there were simulations of sort of Archean Earths and proterozoic Earths as well. But they're carrying the best instruments we can think of. They'll teach us everything you can plausibly learn about their atmospheres within the laws of physics we have right now. And so interpreting them, oxygen complicated, but the mission design, I think, not we, because I wasn't involved in this, but I think the people who did the designs are doing it right. They're designing general purpose planet characterizing machines rather than locked on any single feature.
Right. Yes. Thank you. I apologize for overemphasizing oxygen, but you are right. And there are a huge variety of biogenic gases that can be analyzed. And yes, my understanding is that the wavelength range is meant to encompass those. So thank you.
Bill has a question.
Great. Hey, Niki, fantastic talk. Thank you so much. I really love that. To return back to a previous question about oxygenetic photosynthesis, that may be very difficult and may be tricky to do, may not be particularly common, but do you believe that non-oxygenetic photosynthesis, just photosynthesis, is that inevitable on an Earth-like planet?
That's a great question. I think it's going to be an easier task than obviously evolving oxygenic photosynthesis. So again, they use very simple reductants, hydrogen sulfide. All of their photosynthetic machinery is much more simple. And the pigments, there's different thoughts about sort of the evolutionary pathway of the pigments. But if you were to ask my opinion, I think it's reasonably likely that anoxygenic photosynthesis could have evolved on an exoplanet.
And if I may follow up, anoxygenetic photosynthesis began first. How is it that the more complex oxygenetic kind of came to dominate? If you're in an environment where something evolves and is doing well, how come it's now a distant second fiddle?
Yeah, that's a good question. And a lot of it, again, has to do with the redox potential of water. There's more energy available from that. And also it's just the environmental distribution of water. Water is everywhere. It's more widespread than these other reductants. And so it allows, for example, cyanobacteria in the early Earth to come to dominate so many different surface environments. And even in modern environments today, cyanobacteria are always on the surface. In fact, they're kind of hogging the light. And then the anoxygenic phototrophs are growing communities below, and they're left with the scraps. And so that allows me an opportunity to talk about, again, we think about broad environmental drivers for the evolution of life, but don't forget about these things growing communities. There's a lot of competition within the communities that may actually drive where the pigments absorb. It's because other things are growing above it and absorbing that light, and then the microbes are forced to only absorb in particular band because they're below them. And that ordering of why they're below them sometimes comes as a consequence of their chemical sensitivity. Some of these anoxygenic phototrophs actually don't like oxygen. They don't want to be on the surface. So they're banished to growing underneath them. Yeah, thanks for the question.
All right, I have time for a couple more. Carl has a question.
Hi, thanks. So I have a kind of a basic question because you're a field person. In normal photosynthetic plants, there's a fluorescence signal from chlorophyll fluorescence coming out of the photosynthetic machinery. Is that true of these other photosynthetic processes?
Yeah, I mean, thank you for asking that. So these bacterial chlorophyll pigments do fluoresce, but they fluoresce in the near infrared, where the chlorophyll A fluoresces in the red. It's not exactly as it occurs in plants, but there is autofluorescence within the anoxygenic phototrophs.
Thanks.
Yeah, thank you.
Adam, did you have another question? Adam, you're muted.
No, sorry, I should take my hand up.
Okay. Bruce, did you have another question?
Nope, same problem.
Catherine, I see you have a comment. Did you want? Oh, I guess Catherine's mic wasn't working. So Catherine has a comment in there that we can take a look at.
Okay.
And then should probably be it, because then we're.
I think so.
Okay, well, thank you, everybody. And I'll try to look through the chat and see if there's any questions I can answer there. So again, thank you for giving me an opportunity to chat with you all.
Thank you, Niki. That was wonderful. That was a really, really good, I mean, that was right up the lines of what we wanted to have happen today.
Oh,
Okay.
good.
So our next speaker will be David Kipping, and David will be speaking about temporal and statistical perspectives on our quest for life. So go ahead, David, if you want to share your screen.
Okay, should be sharing now. Great. So this is always a fun opportunity when I get to talk about SETI. I'm sure it's for many of us. It really uplifts me and gets me excited about science when we get to have these days and talk this. So thank you for organizing. I have to admit, when I saw the list of speakers and how much time I had, I thought maybe there was a mistake in the schedule. So thank you for giving me a chance to so much time to talk to you. I thought I would tell you today about trying to spark conversation and discussion, really, and thinking about the temporal aspect. I think we often cast SETI and biosignatures in terms of a search through space, but it could also be thought of as a search through time. So that's really where I want to be generating some thought today. Okay, so I'm going to start talking about temporal SETI, and then if I have time, I'll talk about biases, like selection biases that happen because of time towards the end. We'll see how we do on time. There's an irony there that I might run out of time while I was talking about time. So biosignatures versus technosignatures. I want to start with sort of a little scorecard of some common arguments, not exhaustive, but just some common arguments for and against these different strategies of looking for life. And really they're not, I mean, I'm casting them as verses, but of course they're completely complementary, but I just want to sort of use this as a framework to think about this. First off, just simply going through the Drake equation, you have this FL term, which is a fraction of planets which go on to form life. And it sort of assumes that only a fraction of the biospheres can then go on to form intelligence. So that necessarily would mean that there are fewer instances of intelligent life on a planet rather than just biospheres. Now, of course, that doesn't fully account for the possibility of colonization that we actually heard about in Jason's talk earlier. So if that happens, that could actually lean towards the technosignature case more favorably. But being even conservative, you would say that there would be less opportunities for technosignatures by this logic. The second one, this is probably the one I'll focus on most today, is the lifetime. And again, Jason mentioned this, and we actually heard about it again in Niki's talk just now, that biosignatures, clearly in Earth's record, persist for gigayears, of order of gigayears. And civilization lifetimes, well, we don't know. But I mean, I think you'd have to be pretty optimistic to assume that we're literally at the very start of the story, and we're going to become this civilization which lasts for 1 billion years. And many of us, myself included, are probably a bit more pessimistic about our future, and I might not bet that we would last 1 billion years. So I think there's a broad prior there, but if I think many of us might put our eggs in the basket that probably civilizations don't last as long as biosignatures do. Ambiguity in interpretation is often an issue with biosignatures. Of course, oxygen is one of the things we've just been hearing about as something we can look for, but of course there's been lots of work highlighting, and we've heard about this as well, that biosignatures, especially oxygen, could be a false positive. It could happen through photolysis in the atmosphere, for instance. And so there's some ambiguity in interpreting that. Technosignatures, again, they could be ambiguous, but they also have the potential to be highly unambiguous. And there's a double-edged sword there. There's going to be some unintentional leakage signatures which remain ambiguous, but there is the potential for that prime number sequence that is really difficult to imagine how that could happen naturally. And then finally, in this sort of very simplified scorecard, biosignatures, they don't give you a huge amount of information about the details of the microbiology and the biosphere and the ecology of what's happening on that planet. A technosignature, again, it's that prior stretching out, but it does have the potential to contain a lot of information. You could pack a lot of information into a pulsed laser beam or into the frequency modulation, for instance. And so there is the prospect potentially of learning an awful lot from a technosignature. Now, that's just a scorecard. I think people have strong opinions about all of those, and that'd be great to discuss. As I said, the point of my talk is really to spark discussion. The one I'm going to focus on here is this lifetime. And I'm going to try and challenge this view. Jason has sort of pushed back on it a little bit already. I'm going to try and push back on it a little bit more forcefully in this talk and talk about the idea of temporal SETI. I will also talk about another way that this could be wrong, and that's through recurrence. And that might allude to some of the work we've also heard already mentioned today by Gavin Schmidt and Adam Frank to do the Cerulean hypothesis. So we'll talk about both of these. Okay, so temporal SETI first. Let's just start with the Drake equation. I'm not going to go through it because we all know it, we all love it. But the important thing when I'm writing this out is that I'm writing down the number of communicative civilizations. So this is really N sub C, one might say. And you know, if I'm not just focused on active communication, but just civilizations that last for a long time, and we could be looking for their heat island effects and things like this, then you know we could maybe drop the FC term and just ask how many civilizations are there, period, in the galaxy. So we could drop that FC and have NI, number of intelligences. So that's the number of intelligent civilizations now. Now, the star formation rate, you can argue about this. I'm not going to go through all the terms here, but just for the sake of argument, I'm going to put in of order 1 here. This really depends, you know, we know this number very well, but it depends on the spectral types you're including. Do you include the M dwarfs? We've just heard from Niki that there might be some concern about including those very late type M dwarfs.
So, you mean rate per year? Or?
Yes, this is rate per, this is a rate, so it's number per year. Correct, it's number of stars forming. So in the Milky Way, there's about of order of 1. It's about 1.9 solar masses per year, which is formed in the Milky Way. And so how many stars that corresponds to depends on the initial mass function. And then how many of those do you count as being potentially, have the potential to seed life-bearing planets? You might exclude some certain spectral types. So it's of order of 1. The number isn't particularly important for this argument. So that's the number of NIs of order of this. Now I want to compare that to something else, which we don't often frame in terms of the Drake equation, but can be easily cast. And that's the number of intelligent civilizations ever lived. Drake equation is really talking about the number right now. In fact, it's really the mean number right now. But if we calculate the number that ever lived, and that'll just be the number of stars, and again, it have to be the number of suitable stars. So that, you know, is it the G-type stars that you're including here, or do you go broader? And then it's essentially the same terms, again, all of them except for L doesn't end up on the end of this. We're going to add up. Now by ever, this means both in the past and the future. So that's important to keep in mind. But if we take the ratio of these two, and for the number of stars, I'm going to use 10 to the 10. That's I'd say it's pretty conservative because there's, you know, 2 or 3 times 10 to the 11 stars in the Milky Way. So I'm taking just a fraction of those as being the sun-like stars. And if I take the ratio of these two, lo and behold, we get a lot of cancellations. And so we could say that the number of civilizations ever would be of order of 10 to the 10 over L. This is very, you know, hand-wavy simplified mathematics, but just to give us a sense, order of magnitude of the numbers. Again, that includes some in the future, some in the past, but by that reasoning, you know, we're kind of midway in the stellariferous period of the Milky Way's history. You would expect it to be, if L is much smaller than 10 to the 10, and again, this is in years, just to give you the units here, if L is smaller than 10 to the 10 years, then that would mean that there are far more extinct civilizations than extant civilizations. So this is the temporal aspect of SETI. We know we may be surrounded by, you know, we may not be anyone in the galaxy right now to talk to. We might be the only ones right now. But, you know, even if you're very pessimistic like that, then you would still have a hard time arguing that it never, ever happened in the entire history of the Milky Way. And so you might expect there to be some relics, some out there in the Milky Way to look for. So if we had this L much less than a gigayear, then we should reasonably expect to be more extinct civilizations. Although I have to say both of these numbers could still be less than 1. I mean, N is really like, it can be a fraction. It can be like 0.1. And so it could be 0.1 is much greater than 10 to the minus 6 or something. So both of these numbers could still be less than 1 if you're really pessimistic. But even so, you'd still expect there to be more past ones than the current ones. Okay, so this sort of changes the way we think about SETI. So we might say, you know, SETI's conventionally maybe thought of as a search through space for ETIs, extraterrestrial intelligences. And I'm going to sort of reframe it a little bit here. And I'm not the first person to do this by any means, but I'm just sort of trying to spark this into people's minds that, you know, we can also think of it as going through times. These will be different snapshots of galactic history. And it might be harder and harder to look back into the past. And the key point here is that, you know, space is bidirectional. We can, of course, send and receive messages with a contemporaneous ETI. So therefore, you can have two-way communication. But of course, time is unidirectional. And it's unidirectional in a specific sense that you can only really send messages forward through time. So you can only have one-way communication, but it is still communication. I think that's important to establish. It is still, I think, a form of communication. Yes, you can't have a conversation, but you can still communicate with another civilization in the future, or we can learn from another civilization from the past. I mean, that's really the bedrock of the archaeology and anthropology. So this immediately sort of raises a question. So if you were focused on intentional communication rather than unintentional signals, which might be like leakage, Dyson spheres. I mean, a Dyson sphere isn't built to communicate. It's just sort of an end product of their industry. But if we were thinking about intentional forms of communication, like a radio beacon trying to say hello, then in that case, we can see that for two-way communication, there's the potential for mutual benefit. You know, I can learn from you, you can learn from me. But with time, if you're sending messages through time, you lose that option, right? So now, really, in a direct sense, only the receiver really benefits from this. And so you might ask, why does the civilization produce these signatures in the first place if there's no direct benefit to them to do so? Some ideas, I'd love to hear your ideas about this, but some ideas that come to my mind would be just sort of memory preservation. You know, a record of their existence, you know, like a relic of their achievements. It might even be philanthropic almost, like trying to teach the next generation almost to not make the mistakes they made. Or it could just be, you know, simply an acceptance. You know, if you did a long-term SETI program and you, after many, many thousands of years, you concluded that you really are alone in the Milky Way, your conclusion might be, you know, if I want to communicate, this is the only way it's going to happen. There's no one here right now, but there is a possibility of actually reaching out to someone through time, just not through space. So it might be through sort of grim admission. So in that case, it sparks the idea of doing a time capsule. I mean, this is really what a time capsule is. It's sending a message through time. And when I think about this, it makes me wonder, well, how would one optimize, construct a time capsule? What materials would you use? What orbit would you put it in? Would it be located on the Earth? Would it be located on another solar system body? How would you do this in order to optimize for temporal METI with the intention of sending out a signature through time? So two examples of this that I can think of. There's been some work already suggesting this. Misra, who's on here, has suggested looking for this in the solar system, looking for relics. As you know, they're not necessarily intentional. They could also be unintentional. I believe in his case, he was thinking more broadly. And then there's even been work more recently that I know Daniel on the call has been involved in, that's been trying to, you know, think about how would you look for evidence on the lunar surface with these high resolution images? Could there be anomalies on that surface that might be deliberate beacons that were left there for us to find? Of course, the moon is a very well-preserved surface. It's only really deteriorated by micrometeorites, so it's a far more pristine surface than the Earth's surface. And so there is the possibility that, you know, a past ETI looks at the Earth 2 billion years ago, sees that it has, you know, some potential, or even is inhabited at that time. They might be able to detect that. And you know, 2 billion years is a long time ago, but it's kind of, well, it's certainly long compared to the flight time across the galaxy. I mean, you kind of heard this in Jason's talk, that it doesn't actually take that long on a galactic scale to traverse the galaxy, of order of 100 million years, even at our current speeds. So it would not be unreasonable for somebody to, you know, plan ahead and to send something to our solar system with that intention. Another example, quite different, that rather than any visitation involved, Luke Arnold's famous paper kind of is an example of this, I think. Here, you know, you could think of these screens as being a time capsule. In a way, it's not preserving much information. I mean, really, all it does is flag the existence. You can maybe encode some very simple binary digits, prime numbers perhaps in this, but it's difficult to encode much information in this. But the beauty of this system is it's completely passive. So if you're going to build a beacon that lasts 1 billion years, you probably don't want to rely on mechanical and even electrical parts, because they would deteriorate over time. The beauty of this thing is that it should be, I'm interested in the calculations, how long this could last for. But this could be a beacon that lasts for a very long time that we could search for. So, you know, in thinking about this time capsule, there are different approaches, and it's not obvious to me which is the quote unquote optimal here. But one challenge, just for fun in this workshop, I thought I'd throw out there is I would love the community to think about this. Let us do it. Let's design, not necessarily build it, but we don't have the money to do that necessarily. But let's think about the design of how we would send a temporal METI message, a time capsule through time. I think this would be a really worthwhile experiment to do. I do want to briefly mention that it doesn't always have to be intentional like a time capsule. These temporal SETI signatures could, of course, as I've already mentioned, things like the Dyson spheres. They could just be products of industry, shades built to control climate change. There, Gaidos was thinking about satellite systems around the Earth, as we've already heard about. It could also be effects on the atmosphere and the climate. I believe we now have the first XRP grant in Technosignatures, which is great, which is sort of, I believe, focused on this area. It's unclear how long that would last. Would that really last for billions of years? Or I think it's more likely that would last for of order of 1 million or 2 million years at most, but I'm interested to see calculations on that. And then finally, maybe probes is another way. And again, here, this isn't intentional. So Voyager 1, it wasn't really designed as an interstellar probe necessarily, kind of has that in the back of its mind, but that certainly wasn't its sole purpose. And of course, we've heard that recently speculated about for Oumuamua as a possibility to its origin. So the idea of probes is certainly not new, and there's von Neumann probes and things like this. Bracewell probes could be another aspect to this temporal setting. But just to mention this challenge one more time, I do think this is useful. We did this for radio. We thought really hard about how to design the best radio message. We sent out this Arecibo message. And I guess there's really a couple of reasons why we might do this. One is just it teaches us, it forces us to think about how we would do it and therefore what we might look for. How do you optimize the information content, the interpretability, and the preservation of that signal? And two, we could actually do this. I mean, if you are a bit pessimistic like me, and you're not so, you don't think maybe we'll last for billions of years, this might really be our best chance of communicating with another civilization. So that's one aspect, is the temporal SETI. I do want to mention recurrence as well. I promised you that. And I think it's another really interesting aspect that gives us some sense of optimism here against this criticism that one might levy against Technosignatures. We've sort of seen a timeline in Niki's talk a little bit, sort of that round, that interesting round diagram. I'm going to sort of flatten it out here. And I'm really simplifying things. I'm not a biologist, so this is just putting data points on a timeline. But when we look at the history of the Earth, we might say the Earth becomes habitable 4.4 billion years ago when the oceans first formed. Clearly, there's evidence for life. Pretty quickly after that, you can sort of argue about which piece of evidence you believe, but the most optimistic puts it within sort of 300 million years. And then we have intelligence arriving far, far later. I mean, you can sort of argue about exactly where that point arrives, but it's of order of 100 million years or so within this bracket. It's difficult to push it back. If you push it back 500 million years, that's the origin of multicellular life on the Earth. So you can't really push it back dramatically on this scale. And then going forward, you have the Earth becoming uninhabitable, of course, as the sun evolves and the long carbon cycle shuts down. So I want to just point out some evolutionary points on here, which are, and give us some context for Technosignatures and Biosignatures. Photosynthesis, we've already heard about this, of course, in detail in Niki's talk, so this is a much more simplified discussion of it. But of course, once photosynthesis evolved, doesn't have to have necessarily produced oxygen, but on the Earth, clearly there was a successful pathway towards doing that. And it led to this, well-known great oxidation event on the Earth. Now, the oxygen levels were pretty pitiful for a long time, of only a few percent. It's unclear whether future telescopes could really detect that, or at least our future telescopes, maybe a more sophisticated civilization could detect those. And in the last sort of, as we heard, like 0.8, 0.7 billion years, the levels really rose as all of the oxygen sinks were basically saturated after that point. In any case, there's a fairly long period here where a biosignature should be detectable on the Earth. In fact, if you wrap this all the way over and it continues until the Earth is habitable, it occupies about 2/3 of the Earth's timeline, at least the habitable timeline for the Earth. Okay, so that's pretty sizable. And what's also important to mention is that this happens in the face of mass extinctions, right? So none of these mass extinctions stopped, ended the reign of oxygen life on Earth or photosynthesis. This was a very successful, when cyanobacteria got it and it spread across the kingdoms, this was a very successful adaptation that persisted in the face of mass extinctions. There's just 5 we know about. There's arguably many more than that, in fact, even in the last few 100 million years. And clearly there must be more mass extinctions prior to this that we just don't know about as well, that we can't detect in the record. So these traits persist in the face of mass extinctions. And, borrowing a little bit from Brandon Carter's paper where he talks about these 5 or 6 steps of evolution, these aren't the only important transitions. We have the development of eukaryote cells, we have combogenesis. And the key thing is that all of these persisted, right? If these traits are, this is really the very nature of Darwinian evolution, that if a trait is majorly beneficial, then it should persist and continue to propagate. And so presumably will do so as well until the Earth is uninhabitable, we would expect. Now, what you might now wonder is, could intelligence, Brandon Carter really does claim this. I'm not sure I would be so comfortable claiming this, but intelligence is another example of one of these major evolutionary transitions. Now, if that were so, maybe intelligence is something similar to the great oxidation event. It's a great intelligence event. If this is a trait which is genuinely beneficial to survival, which seems to have been for ourselves, then there's a good case that it would persist. And if it would not necessarily through us, but the nature of intelligence would persist on the Earth. So we have possibly a persistent technosignature in that sense. It's not civilization. So I really want to be clear about this hypothesis. I'm not really talking about civilization lifetimes. I'm pretty pessimistic about civilization lifetimes, but I think the idea of a prolonged intelligence or technosignature lifetime on the Earth is interesting, that it could survive for order of 1 billion years. So that would balance this scale a little bit, not completely, but it would balance the scale a little bit against this common criticism. If we look at the archaeological record of what we know of past civilizations on the Earth, then civilizations don't last that long. This is why maybe I'm a little bit pessimistic. But if you look at past civilizations, they typically last only for a few hundred years. And so, I think there's a good case that civilizations might be ephemeral, but the existence of civilizations has been persistent throughout that time. And so intelligence, could be argued to be a persistent phenomena. Another more kind of lucid take on this would be to say that Earth is infested with intelligence. And how do you eradicate every human being, or a sufficient number of human beings to completely remove our presence, and even the presence of not just us, but all hominid species and all signs of intelligence on the Earth whatsoever? That would seem to take a rather radical event to do so. And of course, this isn't, the idea of a recurrent intelligence isn't new. There's two thinkers here who I want to reference. There's David Grinspoon's quote at the top, he wasn't really talking about intelligence. I'm not sure if he said this about intelligence or not. I know he said this about life, that life doesn't happen on a planet, it happens to a planet. And in the same way, it may be so for intelligence, that it really is a phenomenon which happens to biospheres. Once it happens to a biosphere, it's kind of difficult to stop it. In the same way, it's very difficult to eradicate life. In the past, there has been speculation of a past civilization, and what it would take to detect such a civilization by Gavin Schmidt and Adam Frank, who were thinking about the sort of geological and climate and the atmospheric signatures that one might expect to see from such a civilization. And of course, it's actually remarkably difficult to disprove that such a civilization ever existed. And going forward, we don't know what the future of evolution is. And it's evolutionary biologists, I think, are often very timid or worried about speculating, because it really isn't often thought of as a predictive model, more of an explanatory model of Earth's history. So it's difficult to use evolutionary theory to make predictions, but I think it would be interesting in these discussions to include evolutionary biologists. I know we are including biologists, obviously, because Niki's here, and I think that's a really useful collaboration to continue in anthropologists as well. And when we think about this time capsule experiment, it may be that we are not actually intending to communicate with another extraterrestrial intelligence, but rather a terrestrial intelligence that may inhabit the Earth 500 million years from now, some very, very distant descendants out of ourselves. And so, you know, this is this terrifying mock-up of what human evolution might look up in the future. It may not even be actually directly related to us, but I think that the aspect of intelligence may be difficult to eradicate given the evolutionary benefits it bestows. So to conclude the temporal SETI portion, I would just say, you know, some interesting things I think I'd encourage the community to think about. I know many of you are already thinking about this, is how do we communicate through time? And that's the METI, the messaging aspect, temporal METI. And I think the act of designing, sitting down, designing a time capsule, would you put it in a lunar cave? What material would you use to construct it? How would you signal its existence? Are there orbits in the solar system which are stable for long enough that you could place something there? I think that exercise would be really fruitful and beneficial in our own endeavors to look for these things. And then, of course, actually conducting a search and thinking about how to go the next step and actually conduct such a search would be really interesting too. And finally, if intelligence is a persistent evolutionary trait, then I think the case for technosignatures looks much more favorable than it might otherwise do. If we just focus on human civilizations, I think it's easy to be pessimistic. But I think if you think about intelligence as a trait, it's a more optimistic case. So I probably won't use up all my time, but I just wanted to point out two other ways in which time is relevant to the SETI discussion. And both of them are biases. So there's two biases which creep into search for life in the universe. So what I'm going to show here is a little movie of, it's like a plane of the galaxy, if you like the local stellar neighborhood. And each dot is going to represent a civilization. And if it's a green dot, it means and this is a Monte Carlo simulation really, I'm starting that civilization with a lifetime which is less than the average. Whereas if it's a red dot, it's a civilization which has a lifetime which is greater than the average. So it's got like a predetermined fate of how long it will last. So I'm going to populate this, and they're just going to sort of populate at random times. I apologize, I should have used better color coding. I didn't think about that when I set this up. So I apologize for that if it's difficult to see this. But we have the green dots and the red dots populating. You can see I'm using a 50-50 split. So there's half of them are older than average, half of them are younger than average. We could think of us maybe as being in the average as sort of a mediocrity principle argument. So half of them in the average. But if you look closely, you might notice something. And that's that even though I'm populating these half-half, there appears to be a disequilibrium. And in fact, there appear to be more red dots than green dots in this simulation. So if actually you take a histogram of the two, or really a bar chart of the two, you can actually see that really clearly. There are far more of the longer lived civilizations in here than the younger ones, even though I populated them half-half. And what's happening here? Well, it's the temporal bias. There's, you know, in any given snapshot in time, there's inevitably going to be more long-lived civilizations than how you spawned them, just because they persist. They last for so long that, of course, there's more of them at any given snapshot. So I think this temporal bias of it has some interesting implications. It means if you were to imagine looking around the local stellar neighborhood, then the nearest civilizations to us, most of them would be, you'd expect to be older than the average. And maybe we're at the average, maybe we're not, but by the mediocrity principle, you would sort of expect that. And in fact, some of them would be far, far older than us on this scale, depending on what the maximum lifetime of civilizations may be, if there even is such a thing as a maximum. So this, we wrote this up in a paper with Adam and Caleb Scharf here at Columbia. And we called it the contact inequality. And generally the argument is that, you know, unless lifetimes of civilizations are truncated to be, you know, more than twice our current age, our current lifetime, then you really should expect the majority of extant civilizations, or really ETIs, to be greater than that of our own. Now, I really actually kind of regret this title. I talked to Adam about this before when I visited Rochester recently, because I don't think it's right. I think the work I believe is right, but I just think I made a mistake with the title, because it kind of makes presumptions about detectability as a function of age, which we can't really assume that a civilization in the future, a more long-lived civilization, is more detectable or less detectable than us. So I think a better title, if I was to rename this, and I wish I could, would be that it's an ETI lifetime inequality, that the nearest ETI is likely older than us rather than younger than us. And that's probably as strong as a statement as I'd be willing to make from that. Now, that's a related idea to this was also published soon after us by Balby, and they were kind of more interested in the duration of the technosignatures rather than necessarily the lifetime of the civilization. And again, they kind of come to a similar-ish conclusion from a different perspective, that a long-lived technosignature is inevitably going to be easier to detect. And so there's a selection bias, in effect. When we're looking for these things, we're more likely to hit a long-lived one. Now, I have to say, I have sort of something that concerns me a little bit with that conclusion, and that's whether, well, certainly a long-lived technosignatures, if they exist, would be sort of unambiguous, but whether a long-lived civilization necessarily is more detectable sort of depends on sustainability and the effects of sustainability. And this, again, has been pointed out by some of our colleagues already. Mr. has already suggested this as a possible solution to the Fermi paradox, that, you know, taking Clarke's third law and sort of extending a little bit, as Carl Schroeder did, that any sufficiently advanced civilization may be indistinguishable from nature. I mean, it's if you're in complete disequilibrium with the ecosphere of your planet indefinitely, that would seem to preclude your longevity, essentially, unless you're literally living in a slash and burn type existence of moving from planet to planet. But that seems like difficult to find enough biospheres to sustain yourself, given the limitations of space travel. And Adam Frank's also been thinking about this, I know, and we've had these conversations about what does a billion-year civilization even look like? Are they even something we could detect? And in this kind of extreme, kind of deep time perspective, what are the signatures of civilizations? Another argument would be that, you know, looking at the right-hand side, that actually the shorter-lived civilizations might be by far the easiest to detect, because they're in complete imbalance with their biosphere. And, you know, we've stopped producing CFCs to a certain extent now, at least polluting the atmosphere as much. And we're hoping to cull our effects on the climate. And so if we reach that equilibrium, then we would become less easy to detect through those effects than we would be if we lived in a complete rampant sort of towards an unsustainable future. So temporal bias, I guess my first conclusion from this is that, you know, our neighbors, I think there's a good case that our neighbors could be older than us. I think that's not an unreasonable thing to say. And people have been saying that all the way, you know, back since the dawn of SETI. So that's not a new statement. But I think an interesting unclear future or unclear area is what is the detectability of far longer lived civilizations than us? What do they look like? And in particular, the unintentional signatures may actually go away over time. They may become harder to detect. The final thing I want to mention with temporal bias, and then hopefully we'll have plenty of time for discussion here, is in the Drake equation, this number is really a mean. Me and Jason had an extensive conversation in Twitter DMs about this, because people have criticized the Drake equation for not being stochastic, but really it was never intended to be stochastic. It's really written down, if you look at the terms and the definitions in Drake's paper, he actually defines all these terms as means. It's the mean rate of star formation. It's the mean fraction of planets that go on to, you know, form life and intelligence. So all that mean is really important, because, you know, the actual number of civilizations in the galaxy at any one time is going to fluctuate around that mean. Of course it is, because, you know, that's just the nature of randomness and stochastic processes. So I think that criticism is slightly unfair. I think actually Drake somewhat anticipated that by the very way he frames these as means. He doesn't explicitly call n a mean, but I think it's kind of implicit by the fact he calls many of the other terms a mean. The consequence of that would be, you know, I'm just taking an example here. Let's say the mean number of civilizations was 10. It would follow a Poisson process. It would fluctuate over time, up and down. And you could make a histogram of this, and you could say that the probability curve would have some spread. It has a mean of 10, but in some epochs there are 15, even 20 civilizations, and other times there's hardly anyone around. there's actually a nice proof of this I wrote up in a recent research note that establishes why this has to be a Poisson process that I'll direct you to. Now, kind of an interesting consequence of that is, let's take this fun, simple case where lambda, the mean, is 3. So the mean number of civilizations is 3. And so you can see it peaks at 3, just as we expect. But we can imagine these are different snapshots in time. So in one snapshot, there could be 4 civilizations, let's say, communicative civilizations in the galaxy, n equals 4. But another snapshot, there could be 2. And these are equally probable outcomes according to this particular choice of lambda. So these are equally likely to occur. But of course, this kind of gets into sort of a selection sampling effect and reference sampling. Because you would really expect if you're going to be born in any given country, you're much more likely to be born in a high population country than a very tiny island like Henderson Island in the middle of the Pacific Ocean, just because the population's so much smaller there. And so by that logic, you would expect to be born in an epoch of higher than average population than lower than average population. So this might give us some sense of optimism. And indeed, that's not only true through time, but also true for the region of the galaxy that we live in. You're more likely to be born in the region of the galaxy that's more high populated than average, and the galaxy itself is more likely to be a more, rather than looking at an elliptical galaxy, which might, be of comparable size, there might be something about the Milky Way itself which is conducive to life. So those are really all my thoughts that I wanted to share with you. I really appreciate your time and the opportunity to spark some discussion here. Just to summarize, I think, the temporal SETI aspect is an interesting way to think about how do we communicate through time. And I'd really love to spark discussions about how would you do a time capsule? What's the optimum strategy? And I would love it if we actually did it. I mean, if SpaceX are planning to go back to Mars, to the moon soon, it would be great just to hop a ride and put something on the moon that would be a deliberate, long-lived time capsule. It might be great press for them as well. The temporal bias aspect is the other important component here. And I think it kind of nods the odds, and we have to think about that. Selection biases do come into SETI, and time is maybe a selection bias that we don't usually think about, but the idea of very long-lived civilizations is something that I think is a challenging subject to broach, but one that we deserve to give attention to. So with that, I'll say thank you and take any questions.
Thank you, David. Very, very stimulating. Okay, I'll hand it over to Robbie and Jacob.
All right, looks like Jill has her hand up.
Okay, David, I just wanted to point out that the ARCH mission is doing exactly what you're suggesting with respect to the time capsules. And it is, in fact, at the end of the summer, sending one to the moon.
Whoa, that's awesome.
So I put the link in the chat.
Great. Thank you, Joe. That's fantastic. I'm really excited about that.
Right, Bruce.
Yeah, I like the thinking about what's visible. And given my talk, I was trying to think about what we could do that would be visible as a time capsule of our civilization to hypothetical extrasolar space telescopes. And I think I need about 10 to the 12 tons of material to do that. But if you can give that, we could leave something that would, produce a signal every 1,000 years for a billion years or so. It's probably a minor thing, and I'll have to think about this offline. I'm not sure I believe the argument in Poisson statistics that because we're here, we're likely to be at a time with lots of other civilizations. If you think of it sort of like anthropic principle almost, the fact that we won the get to exist lottery presumably does not create any change in the odds of that lottery getting won in other solar systems. But maybe that's one of those non-intuitive probability occurrences like the Monty Hall problem that you need to think about, but it feels wrong. And so
yeah, I mean, I think the reason why it probably feels wrong is because the doomsday argument it kind of almost borrows from that, right? Because it's and that argument is commonly criticized. Well, what is the reference class you're using there? Is it time? Is it number of years since humanity has been a civilization, or is it number of souls, or maybe the experience of a human in the past is not the same experience as a person is having now? And so it kind of falls over with this issue of how do you decide a reference class. Yeah, I'm not sure. I kind of put, that's not published work. I really put that out there as a thoughtful, to spark conversation, but it would be really strange if we lived in an epoch where, because there's no real external selection bias in terms of it'd be more, unless civilizations go around stomping on each other. That's really that would clearly, eradicate my argument. Yeah. But if civilizations really liked stomping on each other, then you're more likely to live in an epoch where there's no one else around. But if that's not true, then I think, I'd like to think about it more as well. But I think it's more robust than the doomsday argument, is my feeling.
I think for non-stochastic effects, like Milky Way habitability changing due to gamma ray bursts or metallicity or something, or stomping, we're absolutely more likely to live in an era in which the various probabilities of events leading to intelligence occur are higher. I think the pure Poisson thing, assuming that the probability per billion years of a civilization arising is uniform per billion years, there's no particular reason we have to arise at the same time as the other 4 civilizations in the galaxy versus just being the only one. I think you can show that if the rate is really uniform over the history of the galaxy, we don't especially have to be at an outlier in the Poisson statistics either way. But we can take this offline and think about it more and hire a philosopher and drink or whatever is appropriate to resolving these questions. But
yeah, I do. I think it's a very subtle effect. It's not I don't think it's a strong effect. I did work that through. I
think by the time it's subtle, it's not an effect, right? I mean, you can't. But I'm not sure. Yeah, we can.
Yeah. Well, I might disagree on that. I think it is an effect, but I think it's a subtle and small effect. But yeah, I'm happy to discuss more.
Because the events occurring in other systems are independent of what occurred in my system, right? I don't. There's no particular way we can influence what's happened in the rest of the universe through our existence. So the probabilities that event series happened elsewhere in the universe is independent of our existence. I think, but quasi-philosophical. So, all right, and then if someone can give me 1 trillion tons of material, I'll get working on designing a self-replenishing debris disk with characteristic spectral signatures that you can see from a kiloparsec away or so.
All right, Iman.
Sorry, is that me?
Iman, yeah.
Oh, yeah.
Right. Yeah, thanks, David, for a really stimulating talk. I was quite intrigued actually about the idea of trying to devise ways of having kind of long-lived beacons of our existence, etc. And it's good to know that there's projects to send stuff to the moon, etc. I'm quite intrigued that actually exploring that further kind of has implications as well for the Fermi paradox, right? That the more successful we are at coming up with ways to put out, posthumous signals, if you like, of our existence that have a greater and greater permanence, then that L term in the Drake equation, if you choose to interpret it as communicating posthumously, then that L we can get a much larger value for L by thinking about how we would keep our own existence, evidence of our own existence alive in the galaxy for as long as possible after our own existence. So it seems to me to put an even more extreme spin on the Fermi paradox when you think of it that way around.
Yeah, I hadn't thought of it. Yeah, that's a good point. Yeah, so if it's a number of technosignatures rather than necessarily just commutative civilizations, then yeah, you're producing a technosignature that can last for 1 billion years. But of course, the downside would be that you're banking on someone finding it if it was a time capsule. So yeah, that's why the optimization problem is interesting to think about. Like, how do you make this as easy to spot as possible, but also be something which can last as long as you want.
Yeah, but it does bring into focus that actually we can make some inroads into working out what L could be if we interpret it in that way, whereas it's always seemed like the term where you just toss a coin or plug in your favorite number and nobody knows any better. But actually thinking of our own our own permanent signature may be one way of trying to quantify that.
Right, and you presume there are some physical limits which will put upper limits on how long you could make L. You know, what is in terms of the micrometeorite erosion, or just literally the atoms sinking under gravity and collapsing that box into a pool on the surface of the moon, things like this, or neutron erosion. You know, there's these effects should place limits on how big L really could be.
Jill, do you have another question?
Yeah, it had to do with Bruce's comment that our existence here can't in any way affect any other civilization. And I wonder if that's true. I often think about what if the distribution of civilization or technology lifetimes is bimodal, with a lot that are short-lived and a few that manage to make it through to a long-lived, stable situation. Perhaps SETI and the detection by a short-lived potential civilization could in fact impact the probability that you could become a long-lived civilization through motivation or just proof of concept that it's possible to be such.
Yeah, and that would of course also put tension on the Poisson. It would formally make the Poisson process wrong, because it would mean the Poisson process assumes there are independent processes. There's no communication, there's no influence between the events. So yeah, any interaction would eradicate that. But that's the idea of bimodality I hadn't thought of. I know in Adam and Caleb's paper of mine, we suggest an exponential distribution, just as sort of a simple first stab at it. But that the consequence of an exponential distribution is that you're assuming there's a constant hazard rate. So the risk of you going extinct in any given century is the same. And it's not obvious that that's a valid assumption, but if you want to build a more complicated model, then you're left wondering what on earth to assume for that, how that changes over time. But you're right that it's not unreasonable to think that once you get to a certain point, you become almost indefinite. But then I get that comment a lot on my videos sometimes. I always say, well, our technology doesn't necessarily make us safer. I mean, you might argue that it's put us more at risk with our growing technology as well. So it's not immediately obvious to me that it's always beneficial, just going out to that long tail.
Let's go to Jason.
Great. That was really neat, David, all these cool ideas about longevity. One thing I just want to point out when we talk about these discussions about the long future, especially if we think about life spreading through the galaxy and being in multiple places, is that we're not talking about like one civilization taking over the galaxy, especially once you start separating, a species temporally and eventually spatially, because light is slow, you're going to get divergence. And so in that video, I showed all the things turn magenta, but presumably all of those magenta dots throughout the galaxy are effectively independent. And while they can communicate, so they're not independent in the sense you mean, in terms of, whether they can influence each other's L. But in terms of like, their motivations, what they're going to do, we should be very careful to, think of them as a civilization. I mean, even Earth is not well described as a civilization, right? It's a lot of people doing independent things. And a lot of the biggest things we do are not well organized, right? The increase in CO2 in the atmosphere is, is a poorly organized thing that is happening, and we're trying our best to avoid, right? And so I think a lot of, when we try to do these projections, we have to make sure we're imagining, lots of species, lots of civilizations, lots of motivations. And what persists, like you said, is the intelligence. And so that's why I really liked your idea of the recurrence, that what matters isn't that our civilization survives, whatever that means. All that matters is the technology does, and that can be detectable, because that's the only thing we're looking for, right? We're not looking for intelligence, we're looking for technology.
I think what you're extending is to take David Grinspoon's comment to a third level, is that intelligence isn't something that happens in a galaxy, happens to a galaxy.
Right.
It is a phenomenon which, yeah, in the same sense that there's all these civilizations on the Earth which have come and gone and collapsed, the existence of civilizations has been a persistent phenomenon since its first instance.
Right, and more relevantly, it's the technology that has persisted, and even if it gets put down for a while, its relics are there and it can be picked up again.
Yeah.
We still make glass the way the Romans did.
Right. Yeah. Some technology is just permanently useful.
But as I threw out in the chat, glass may not last for gigayears, but zircons do. So maybe you should learn how to etch Encyclopedia Galactica or Britannica into zircon if you want a good time capsule.
Yeah. Yeah, that's interesting. I did do some cursory look into the materials, and my guess was you'd want a very dense metal, something like tungsten or something like this. But yeah, I'm not aware of any serious calculation. I know I asked Adam this when we were chatting, like, how long would the Apollo missions last? And I don't know of any good calculation of that, of how long that technosignature lasts.
Yeah, I think there it's the erosion from micrometeorites, but
Which would be very slow.
David, I think the best example of your time capsule might be the Voyager records. They were designed to last basically forever.
That's true, but the problem, I suppose, with the Voyagers, it's very difficult to discover because they're.
That's right. They were in orbit around the sun and reflective, as opposed to just drifting into the middle of interstellar space. Then maybe, yeah.
Right, and then again, that raises the question: well, which orbits in the solar system are actually? I mean, people calculate satellite orbits for tens of years and hundreds of years, but rarely are they propagated for that long. So
you want something very far out to something.
People run these multi-billion-year solar system stability simulations, so it'd be easy to plop a satellite into them. And generally speaking, all the places there are planets are stable on multi-billion-year timescales. I think you'd want to put something. There's kind of a nice dead zone for dust in between Jupiter and Neptune, so probably you get the lowest micrometeorite impact rate.
I think the way to say it is that the places where there's a lot of debris left are long-term stable. The fact that there are very few asteroids between Jupiter and Neptune prove that.
Well, that indicates short-term, right? Yeah, there's an obvious trade, right? Anywhere there's lots of junk.
Things have been perfectly fine for 5 gigayears. Yeah.
Well, some of them have, other ones haven't. The Parabella is self-stirred. So you have to be a little careful about the orbits, what you think is stable. You have to, a lot of them aren't. They move around a bunch.
It seems like we should be talking to the people from the ARC Foundation, because I was just looking at their website. I don't see, I haven't seen explicit calculations, but I would imagine they've thought this out. Like somebody's done exactly the calculation that David and I were talking about. How long would a big black monolith last on the surface of the moon if you put it, made out of your favorite metal? It's easy to imagine it could be quite long-lived. I just want to make one more point and then I'll step back. But just, the idea of the service worlds, which is something that, in the CATS collaboration, we're really interested in. And the service world, if you cover a moon or a non-biological world or non-biospheric world with solar panels, right? How long that could have a huge technosignature, and the civilization dies. And then, all that's happening is there's just spallation and micrometeorites. Could that last, 100 million years as an active technosignature? And so I think that, that may be that really separate, especially when you get to planetary scale technosignatures, which are, again, decoupled from the biosphere. Now you're talking about technosignatures that really have nothing to do anymore with an extant civilization that might be bright and easily detectable and last, on potentially gigayear timescales.
So Ravi posted in the chat, he said moon artifacts would be about 10 to 100 million years.
Well, I mean, one issue is tourism, right? Bodies that are quite close to us are going to get visited by us fairly soon, especially the moon. So, the natural lifetime, I think, may be much longer than the unintentional destruction lifetime.
Yeah, I guess you could have protected sites, but yeah, I take that point. Yeah, and so that then you might think that all bits are referential.
Can I ask, Catherine has a point here, it's a comment. Catherine, do you want to speak out a little bit? I think it's an interesting
Well,
one.
I think Catherine.
Sure, I can try, see if my connection is working. I was just asking about different reactions to extinct versus extant life, given the different probabilities of detection. I think it's an interesting question. Because usually when I'm talking with people about potential reactions to a detection, they're assuming that it would be extant alien life because of the popular assumption of visitation, et cetera, et cetera. There's this assumption that we do in fact coexist in time with aliens and that we could actually have a chat with them. What you're outlining here is what I have for a long time assumed, which is that yeah, our likelihood of convenient coexistence is not necessarily that high, but it changes the equation in terms of potential reactions. But it also changes the challenge about how do we differentiate, as one of the other observers noticed, like how do we actually tell the difference between an extinct and an extant society? But anyway, that was just something I wanted to throw out for just general discussion.
Yeah, and I kind of also wonder about the other side of that coin, of the messaging side. People might, I think there's discussions about how the public feel about sending messages to other civilizations that may be around us right now. But how would they feel about the concerted effort to build a message through time? I mean, maybe we're so selfish that there's just no interest in that whatsoever, or perhaps people feel more at ease with that idea because there's no risk of retaliation or something, you know, some kind of knock-on consequence visitation.
That's a good point, David. I think there's traditionally a lot of interest in time capsules. I mean, when you think about it, the number of things that humans do for the sake of posterity is very great. I mean, essentially every form of writing that we have, that's what it's all about at the end of the day. Right. So it may be that there's actually less of a barrier to that kind of idea than there is to the idea of communicating in real time.
Hi, I wanted to point out a paper that was in 2006 by Rose and Wright in Nature that wasn't referred to, that was pointing out that if you sent a capsule that could survive for hundreds of millions of years, and that seems likely, you could put the equivalent of a flash drive in the middle, protected from cosmic rays and such. And you could send the same information rate as you would send with a radio signal over the same time. It just takes a long time, but the bits per second, once it arrived at its destination, would be about the same. And so it's a rather interesting idea. If you seed the galaxy with these kind of things, you could be sending the information all over the place, and it might be that we can communicate that way rather than through the usual kinds of radio frequencies.
Yeah,
I need to drop too, but that was a great idea. I just wanted to throw something out. What if that does happen and that early civilizations actually pass on a little bit of lessons learned so that later civilizations can actually last longer? We usually assume in the Drake equation that the duration of a civilization is independent of time. It's just it's a constant. We just throw it in there. But maybe there's a learning curve, or there could be a learning curve if there are some of these time capsules.
That's right. Well, essentially it becomes one larger civilization that is taking place, just like on Earth, where the whole world is speaking English.
Or if we were to find a bunch of time capsules and we figured out that, oh, 3/4 of civilizations killed themselves in nuclear wars, so then we'd learn to avoid nuclear war, for example.
So I see Glenn has been patiently waiting. So Glenn, thank you. Could you want to talk?
Yeah, real quick. Stuck. I remember I said I was stuck on the interstellar medium. So clearly, about 4 billion years ago, the chemistry was right, such that life could form on the Earth. So that's sort of a lower limit. But it turns out that the Big Bang has been progressively making the universe accessible colder. And there's already known in the interstellar medium that only certain there are certain processes that can only happen in super cold environments. So that it may be that there really was a sort of a time zero that is, maybe 8 billion years ago or whenever it was when those chemical processes could lead to life. So I think there is another possibility that, maybe we're not one of the fields, but we're all all of the civilizations are just blooming now because they all started about the same time, because when the chemistry would work. So anyway, that's I think there may be another sort of a lower limit because you couldn't get the chemistry you would need to make life before at least some time. I'm not sure, maybe not work with 14 billion years, but whatever that temperature is that does allow the chemical processes to work. So that's just a comment, but I do appreciate all the talks so far. Thanks.
That's really cool. Do you have a reference for that idea? I'd love to hunt that down.
Well, I just made it up, so I'm not sure, but I'll.
Okay. Oh, that's a really
It's
fascinating.
like temperature inside a molecular cloud isn't really going to be set by cosmic microwave background so much as heating from the rest of the galaxy, I think. Metallicity is an evolutionary thing.
No, I think that's not quite right because you have to be able to get to a cold temperature, right?
Right.
So I don't think it's if having a cold temperature is critical, which is a hypothesis, it's not proven. But then you couldn't get to a cold temperature if the universe was too hot for that. Anyway.
I guess because it's microwaves, it penetrates deeper, right? Yeah, most of the energy density in the galaxy is starlight, but starlight doesn't make it to the heart of a molecular cloud, and the CMB does. So, yeah, but it hasn't been that long since temperatures drop so fast, right? That the CMB's been below 6 Kelvin for a lot of time, many billions of years. So. Yeah, be an interesting calculation. I apologize for quickly rejecting because I didn't think about wavelengths. But
I just think there is an exoplanet side to that, and that's there's the metallicity correlation, and so of course you may not have rocky planets at a beat below a certain point in the galactic history. So although it appears, I think there's no counterexamples to that. It appears that no matter how old a star you look at, we always seem to find planets.
Right, the strongest observed metallicity correlation is for hot Jupiters, so it doesn't necessarily tell anything about Rockies. And then the sun is giant, yeah, and the sun is weirdly high metallicity for its age, isn't it?
I think so.
A little high. Okay.
Not really.
It is 5 o'clock now, and we still have we had set aside 15 minutes for discussion at the end, which we kind of were hoping was just, we could continue the conversation we're having because God knows it's interesting, but also to sort of think like, what to do next, or where, how can we build on this? We've had 4, really excellent talks and lots of conversation that have come from them, including some nice cross-fertilization with biosignatures as well. So I guess I just want to, just see if anybody has anything to think, how do we keep, what might next steps if we wanted to systematize, because that's from the CATS grant, what we really are trying to do is think about sort of the maturation of technosignatures as a science. So let me just turn it open if anybody has any ideas for that.
Eamon.
Yeah, so going back to Jason's talk where he was mentioning about people like Frank Drake and that, stressing how we have to align SETI strategies with let's say standard scientific goals, that there should be other, it shouldn't all be eggs in one basket. We either detect aliens or we don't, but there should be other ways and other measures of success in terms of what we can do with the data sets we accrue. So I'm wondering whether one way forward would be to have a kind of like, I don't know, mini competition, if you like, to draft some proposal, fictitious or otherwise, about a SETI related project we'd like to get off the ground, which could achieve certain other scientific aims as well by the design of the survey or whatever the project is, and kind of see. I guess what we'd all like to see is some way of getting funding streams for this kind of work. But obviously, I guess the success of that will
be contingent on being able to show that there is some pretty amazing science aside from SETI, which, you know, I guess is still very hard to fund.
Jill?
The last name is Paul, K-O, so Paul.
Jill, I see your hand is raised.
Yeah. So I would think that maybe a good next step is to stop just doing what I do, which is wave my hands, when thinking about all of these new astronomical facilities that are going to come online, and actually do some calculations about what they might do in terms of providing sensitivity at wavelengths or in different parts of the parameter space that we haven't looked at. And then think hard about what it would need, what we need, and that's what Iman was talking about, to actually modify those instruments, or at least make sure that the possibilities for doing searches for technologies aren't designed out.
Right.
So some of us actually in the CATS group that Adam and Jason and Jacob are doing, we're looking on one part of that, which is the atmospheric spectral features of for nearby missions, using, you know, for James Webb or with LUA or HABEX. So that's one aspect of what you are suggesting as a broader facility. So there may be some with, you know, Plateau from European side, or from Kiobs, or some other, you know, transit features. So it would be good to have those kind of studies done with other facilities, like you said, even with Roman would be good. I haven't seen a paper that discussed about what Roman could do for technosignature science. Oh, David, sorry, go ahead.
I'm wondering about overlap between the waste heat work that Jason mentioned, and, for example, looking for debris disks, and from the exozodiacal light and optical SETI, is characterizing exozid have some overlap with the optical SETI goals. So it's just thinking about whether either of those aspects have strong overlaps that might enable something like that with photometry.
Yeah, for sure. As we move on to look for like Dyson spheres in the galaxy or put upper limits on them, we're definitely going to have to work closely with the people who work on debris disks, because that's our primary confounder. Gaia lets us finally do this for the first time. And actually, Matt Povich just sent me a list of infrared NExSS stars that came out recently. So I think there's a lot of fruitful stuff to do in that direction.
Yeah, it'd be great if there was, like, maybe it's ambitious, but a James Webb program that was focusing maybe on the disks, but you could piggyback a Dyson sphere search into it.
Absolutely. Yeah, in fact, I mean, piggybacking on debris disk stuff, I think is the right way to go there. We're hoping to work with Disk Detective, for instance, to do a lot of vetting of things they don't think of as interesting for debris disks, but I think of interesting for Dyson spheres. Yeah, and I would love for this group, especially those of you that are really interested in this, to find ways to stay engaged. Hopefully we can do another one of these to keep things going. Please contact us if you'd like to join the Slack. The Goddard Technosignatures seminar, Ravi, I think that's going to continue to be online, right, next year. So that's an online weekly seminar on technosignatures. Ravi can get you on that list. But yeah, please tell us that you'd like to stay in touch, and we can give you lots of ways to do that.
And someone just asked in the chat if the talks are recorded and available online. Yes, the talks are, well, we're still recording right now, but we've recorded all of the talks. And once we've, cleaned them up a bit, we will post these on the NExSS website and the NExSS YouTube channel. And when we've done that, we'll send out an announcement as well. So if, however you heard about this event, you will hear about the talks as well.
Oh, and the Slack channel for if people want to join that, please let us know.
And that's TechnoClimbs. We might want to send that out again because it's very deep in somebody's,
So everybody who's emailed me has already been added to the Slack, but yeah, email me if you want access to that.
And one thing we could think about is doing something like this again in another 6 months, but maybe a little bit more focused. Maybe it's David's idea about the challenge to build a time capsule. We could, and so we'd be looking for suggestions, something along these lines where we, do a couple of talks on a specific idea. Maybe it's another possibility is this idea of like, let's go through all of the missions that are coming up and let's ask ourselves for each one of those missions, what needs to be included for them to be Technosignature ready, So I don't know. There's a bunch of ideas have come up, but we could plan on doing something like this again in some number of months. That's more focused.
So I think someone suggested this, maybe Sean or someone, that it would be good to have something similar to what astrobiology has done for origins of life, and have some theoretical foundation for these evolution of complexity and intelligence, something like that. So it was Sean's idea, not mine. So I'm just relaying Sean's words. So I don't know if Sean is still online.
Yeah, that would be, God, that would be something I would love to work on. And, Sarah and I have talked about that. And this is, the David Grinspoon as well. We've talked, so yeah, there's a whole range of stuff like that of it's like psychohistory. How do civilizations form? What's the network dynamics that makes civilizations form and last?
Adam, don't you need to be a little bit more precise about whether you're talking about civilizations or technologies?
Well, I guess you'd have to think about, so you'd have to convolve that with technology use. So you'd have to actually think about the material networks, perhaps, or the energetic networks that allowed you to harvest energy from your surroundings and use that. In some sense, technology is an energy amplifier or a force amplifier. You could think of it in terms of dissipation. You have to harvest energy, funnel off the free energy, not kill yourself with dissipation. So I don't know how this would be done. I've only thought about it only in the broadest terms, but I think it could be very interesting. And who knows, might have things that lead to chemical network signatures of the kinds of stuff that Tessa and Sarah Walker have thought about in terms of downstream. Well, once you do this, what do the chemical networks, the topology of your chemical networks look like in an atmosphere?
Sean?
Yeah, Ravi, this is a follow-up on the question you were asking. I had to get a minute to turn my headphones back on. Where I was going with that is it was building an analogy to the astrobiology program, or for parts of the astrobiology program, or thinking of that as how it's evolved over time, which is if you were looking for funding, my thinking was what would that look like if the funding wasn't just for the technosignatures themselves? And this is me coming at it with my biases as someone that's been involved with or funded by the astrobiology program. I think about the analogy with origins of life research, which the astrobiology program funds. Would that be investing into research into the evolution of complexity or intelligence? What would a really big interdisciplinary endeavor look like, I guess, is the question. Maybe at the tail end, the theoretical foundations all boil down to know your thermodynamics, but I'm thinking about it kind of more broadly than the signature itself. Also the evolution of the planetary system, the original planetary system that would give rise to the civilization, even if it doesn't stay there.
Sean, I think it'd be cool to think about the future of Earth. That might be a really nice, broad, interdisciplinary topic that would involve biologists, anthropologists, and some of these technology arguments as well. So that could be a nice broad umbrella for all of those.
Yeah. Maybe that's an idea for another webinar in 6 months. And let's get some anthropologists. We have some here: anthropologists, social scientists, network theorists. People who work on climate. So Jacob's been doing a lot of work with George on the scenario analysis, which is what the IPCC uses to think about the future in 100 years, even though you don't know what the technology is. So there's people who think about how to think moving forward in fans of history, not deterministic trajectories. So that might be a fun thing to do.
I think, Adam, that there's an institute at Oxford that has exactly this topic. And
Right.
so if you're going to do that, we certainly should include them.
Right.
Bostrom Institute, I think.
Yes.
Well, also the future of the sun.
You have to fold that in, right? Because you have to, depending on the time scale.
Well, we've been talking about billions of years.
Yeah.
I would be very interested to see what is the latest really on how the sun's going to evolve, and then fold that into how that would affect an atmosphere and so forth.
Jim?
Yeah, I think just to go back to something that I think Jill said a few minutes ago, is there any low-hanging fruit in terms of current missions or data sets or programs that we aren't tapping into? I mean, just looking at the thumbnails and faces on this call, I think there's a pretty good span of both radio and optical and infrared expertise, but does anybody have a sense of some obvious piece that we're not tapping that we should be worming our way into to try to make SETI part of the sort of programmatic goals everywhere?
Well, I mean, Tess is going to be is in the middle of survey. Second phase is going to be doing the Earth Transit Zone, right? So that's an obvious target. Yeah, I mean, my pet desire would be, a deep survey of the Earth Transit Zone, especially targeting low luminosity stars. I think from a SETI point of view, that would be quite a good thing to do, and then following up potentially habitable target planets from those.
Yeah, I mean, I see Dan Giles on the call here, and I know he and others are thinking about tests, and certainly tests in the next phase. So, yeah, what are the I guess there's an opportunity there to accompany it with deeper surveys like ZTF has done, sort of following tests around in real time, for example. But yeah, I don't know. It's just something that occurred to me, is that if we want it to be all places all the time in terms of our reach of opportunities and different technosignatures to look at it, there must be data sets and projects we're not connected to. And so that's, yeah, I don't know if there's not an easy answer there, but it's something to keep in mind.
All right, well, it's 5:16 and we've all been, we don't want to stress anybody's, patience or whatever, endurance much longer. So I thought this was very successful. I want to thank everybody for spending the afternoon with us. I want to particularly thank the speakers for really, really engaging talks that achieved exactly what we were hoping for, which was lots and lots of conversation and good ideas. So I think we'll close it here. Yes, applause for everybody, for the speakers and the people who asked questions and the people who hung out with us. So we will all hopefully meet again in the not too distant future on Zoom or in reality. So, all right, everyone, take care.
Thanks, everyone.
Maybe we can stop recording.